From the Southeast Asian capital city of the Philippine Islands, the Philippine nation, Manila. Good morning, good afternoon, good evening. Every single time zone around the earth covered by this, the largest program of its type in the world. It's called Coast to Coast AM. I'm Art Bell. It is indeed a pleasure to be with you on this second day of the weekend. By the way, coming up next week, I have a 3-day weekend, which for me means working 3 days. George will take a very well-earned day off, and I'll pull an extra day. And I've got, I think, quite a few additional days coming toward the end of the month when we will do the yearly predictions that were locked in fact, actually left in the Bell family vault back in Nevada. Fortunately, I was able to, people are amazing. You know, people actually documented the list of predictions made for this year and had them on the web. So I just sort of rummaged around and found a list that somebody had made, a good, nice, accurate, in fact, written, typed out in a much clearer version than my handwriting ever produced. So I have the list, and we will be making predictions, of course, at the end of the month for the coming year. It should be very, very interesting. Again, tonight, that little minx, Dolly, is, she's our new kitty cat. I guess it was inevitable. I'm a sucker for cats. You know me. Erin, by the way, is the exact same way. It was kind of a funny scene. When I first brought Yeti and Abby over here, they came out of their little transport cages, and Erin was scared to death of them, as most Filipinos, and rightfully so, are scared of cats, because here they scratch and they are kind of mean because they're street cats and they get in fights and they just don't, they're very leery around human beings. Well, it took just a little while, and of course, as you well know, my cats, of course, are sweeties and don't bite and scratch and all that. And Erin fell in love with them, and she became as much of a cat person as I am, if not more. And then we met Dolly. I told this story last night. Every time we'd go to the restaurant over here, we'd run into this little minx of a cat that, unlike all the other street cats, would come up and rub on our legs and just do little twirls and twists and just be so cute. And so there was no way around it. We brought her once back to the condo, gave her a bath, welcomed her to the house, and then came to our senses and said, no, we can't do this. And so a couple of hours later, we took her back, put her right back in the very same area, and then 2 more weeks of walking past and meeting Dolly every day was too much. And so the other day, we brought her home for good. She went to the vet, got her shots, got tested, by the way, for those who are asking, got her shots, and she's well. And now she is the 3rd cat in the condo, and she's just a darling, just a darling. Now, Abby loves her. They've been playing nonstop. In fact, you may hear them whizzing by. Yeti has not quite accepted her, although over the last couple of days it's been getting better, and he's hissing less. So now Dolly's proximity to Yeti, I would say when there's a foot or two only separating them, he will hiss. Prior to that, it didn't matter. She could be in the other room and he was hissing. Oh, he was angry. He did not like the prospect of another cat around one bit. But he is slowly, it appears, adjusting. All right, let's take a look at the news, such as it is. While President Bush acknowledges the need for major changes in Iraq, he will not use this week's Iraq Study Group report, which is going to be kind of negative, I guess, as political cover for bringing the troops home. His national security advisor said Sunday, quote, "We have not failed in Iraq." Stephen Hadley said he made the talk show rounds and, quote, again, "We will fail in Iraq only if we pull our troops out before we're in a position to help the Iraqis succeed," end quote. And I do agree with that. And again, for those of you with no memory of it, I was very, very much against the Iraq War prior to our getting there. And after getting there, I feel that we have to find a way to honorably succeed, honorably extricate ourselves eventually, and hopefully leave some sort of better government than was there previously. President Hugo Chavez won re-election by not a little margin, but a wide margin Sunday, giving the firebrand leftist 6 more years to redistribute Venezuela's vast oil wealth to the poor and press his campaign to counter U.S. influence in Latin America and beyond. Challenger Manuel Rosales conceded defeat but vowed to remain in opposition. During the campaign, he accused Chavez of edging Venezuela towards authoritarian rule and warned the president could undertake even more radical policies should he be reelected. Speaking of elections, Senator Hillary Rodham Clinton met on Sunday with New York's Democratic governor-elect to solicit his support for her now very likely White House bid. It was inevitable, wasn't it? The latest indication she's stepping up plans to join a growing field of potential contenders for 2008. Wow. It's getting cold back in mid-America. 4 die in Missouri as temperatures plunge. Frigid temperatures contributed to 4 deaths Sunday, pushing the toll from a devastating ice and snowstorm to 19 as hundreds of thousands waited yet another day for their electricity to be restored. I know the feeling. As temperatures rose into the 20s, Tawana Jean Cooper and her family sat at a Red Cross warming center in St. Louis, which they reached a day earlier from her suburban home after roads were finally cleared of ice, down power lines, and broken tree limbs. By the way, the death toll I am hearing now from credible sources here in the Philippines from Typhoon Durian is approaching 1,000, if not passing it already. It was truly an awful storm here. General Augusto Pinochet, whose 17-year dictatorship carried out thousands of political killings and widespread torture, was fighting for his own life in a Chilean hospital Sunday after suffering a heart attack. Doctors said, though, his condition is improving after an emergency procedure to restore blood flow to his heart. Doctors initially had said they planned bypass surgery on Sunday on the 91-year-old former strongman, but they later ruled it out, saying angioplasty apparently had done the job. The nightmares didn't start until months after Alicia Flores returned home. The images were stark. They were disturbing. In one dream, a dying Iraqi man desperately grabbed her arm. In another, she was lost in a blinding snowstorm. Make that sandstorm. They don't have snowstorms there. Sometimes Flores awakened to discover her mouth was dust dry, as if she were stumbling through the scorching 120-degree desert. Britain's senior law enforcement officials said Sunday an inquiry into the death of a former KGB agent has expanded overseas, and a U.S.-based friend of the former agent said he told police the name of the person he believes orchestrated the poisoning, said he had known the poisoned ex-spy Alexander Levitko since 2002, spoke with him on November 23rd, the day he died following his exposure to a very rare radioactive element, polonium-210. And finally, more than 380 passengers and crew aboard the world's largest cruise ship were sickened by a virus during a 7-day Caribbean cruise. According to officials, the norovirus sickened 338 passengers and 46 crew members of the Royal Caribbean's Freedom of the Seas, and apparently they only needed to be treated with over-the-counter medication. In a moment, as Paul would say, we'll look at the rest of the news. Well, I told you I would mention this again. The apocalypse has a new date, 2048. That's when the world's oceans will be empty of fish. This is a prediction by an international team of ecologists and ecologists, thank you, and economists. The cause, the disappearance of species due to overfishing, pollution, habitat loss, and climate change. The study by Boris Worm, a PhD of a university in Halifax, Nova Scotia, with colleagues in the UK, US, Sweden, and Panama, was an effort to understand what this loss of ocean species might mean to the world. The researchers analyzed several different kinds of data. Even to those ecology-minded scientists, the results were an unpleasant surprise. Worm said, quote, "I was shocked and disturbed by how consistent these trends are beyond anything we had suspected. This isn't predicted to happen. This is happening now," according to Nicola Beaumont, PhD of the Plymouth, Maine Laboratory in UK. If biodiversity continues to decline, the marine environment will not be able to sustain our way of life. Indeed, it may not be able to sustain our lives at all. Already 29% of edible fish and seafood species have declined by 90%, a drop that means the collapse of the fisheries. But the issue isn't just having seafood on our plates. Ocean species do a lot of things that you don't know about. They filter toxins from the water, for example. They protect shorelines. They reduce the risks of algae blooms like red tides. A large and increasing proportion of our population lives close to the coast. Thus, the loss of services such as flood control and waste detoxification can have disastrous consequences. The researchers analyzed data from 32 experiments on different marine environments. Then they analyzed the 1,000-year-old history of 12 coastal regions around the world, including San Francisco and Chesapeake Bay in the U.S., the Adriatic, Baltic, and North Seas in Europe. Next, they analyzed fishery data from 64 large marine ecosystems. And finally, they looked at the recovery of 48 protected ocean areas. Their bottom line, everything that lives in the ocean is important. The diversity of ocean life is the key to its survival. The areas of the ocean with the most different kinds of life are the healthiest, but the loss of species isn't gradual. It is happening fast and getting faster, the researchers say. Worm and his colleagues call for sustainable fisheries management, pollution control, habitat maintenance, and the creation of more ocean reserves. They say it's not too late. We could turn it around. But less than 1% of the global ocean is effectively protected right now. That's less than 1%. And if we do nothing, by 2048, no more fish. The Earth has a fever that could boost temperatures by 8 degrees Celsius, making parts of the surface completely uninhabitable and threatening billions of people's lives, according to a controversial climate scientist on Tuesday, James Lovelock, who angered climate scientists with his Gaia theory of a living planet, then alienated environmentalists by backing nuclear power, said a traumatized Earth might only be able to support less than a tenth of its current 6 billion people. We're not all doomed, he said. A lot of people are going to die, but I don't see the species dying out, he told a news conference. A hot Earth could support much over 500 million people. Almost all of the systems that we've been looking at are now in positive feedback. And soon those effects are going to be larger than any of the effects of carbon dioxide emissions from industry and so on around the world. Scientists say global warming due to carbon emissions from burning fossil fuels for power and transport could boost average temperatures by up to 6 degrees Celsius by the end of the century, causing floods, famines, and increasingly violent storms. But they also say that tough action now to cut carbon emissions could stop atmospheric concentrations of CO2 hitting 450 parts per million, equivalent to a temperature rise of 2 degrees Celsius from pre-industrial levels, and save the planet. So all of these stories that I read seem to indicate that if we don't do something, we in fact are doomed. However, all of this appears to be, and that's a careful word, appears to be reversible if we do something soon. Evidence of flu viruses frozen in Siberian lakes has prompted researchers to examine the possibility that global warming may release microbes locked in glaciers for decades or even centuries. Our hypothesis is that influenza can survive in ice over the winter, then reinfect birds as they come back in the spring. This according to Scott Rogers of Bowling Green State University in Ohio. He believes the frozen lake acts as a melting pot for flu viruses, allowing viruses from one year to mix with those from previous years. Rogers has spent decades searching the ice for microorganisms. He teamed up with Danny Shloem at Bar University Israel, David Glazinski at the Russian Academy of Sciences. And what they have decided is that indeed these influenza viruses can survive. And when you combine that finding with, of course, global warming, then you really have a very, very potentially serious, even deadly apocalyptic situation for the Earth. Well, when you look at all of these stories, again, I wonder what you, all of you out there, conclude. I know a lot of you sit out there and say things like, oh, this is just the sky is falling stuff, yet another sky is falling story. Well, the hits keep on coming, folks, and it seems to me if we don't do something, the sky, well, it really won't fall, of course. It'll simply be a situation where the Earth will not support our life. So the sky might as well fall. Metaphorically, it is in fact falling. Scientists have now levitated some small animals using sounds that are, well, uplifting. In the past, researchers at Northwestern Polytechnic University in China used ultrasound fields to successfully levitate globs of the heaviest solid and liquid iridium and mercury, respectively. The aim of their work is to learn how to manufacture everything from pharmaceuticals to alloys without the aid of containers. At times, compounds are simply too corrosive for any container to hold, or they react somehow or another with containers in other undesirable ways. So it's interesting. They managed to hold this stuff in midair. They levitate it so that it doesn't have to be in a container that it would eat through or interact with in some ways. And now they have managed to, I suppose, for their own reasons, levitate things like ants, beetles, spiders, ladybugs, bees, tadpoles, and fish up to a little more than a third of an inch long in midair. When they levitated the fish and tadpole, the researchers added water to the ultrasound field by every minute by using a syringe. So here you have, if you can picture it in your mind, you have this little fish levitating in midair, just hanging in midair, and the scientist taking a little syringe and adding water, which also levitated around the fish, I suppose, making it environmentally comfortable. Oh, what an age we live in, huh? The dinosaurs, along with the majority of, just I'm thinking of that fish and a scientist injecting a little water around it. The dinosaurs, along with the majority of a lot of other animal species on Earth, went extinct about 65 million years ago. Sometimes scientists have said that the impact of a large meteorite in the Yucatan Peninsula in what today is Mexico caused the mass extinction, right? While others argue that there must have been additional meteorite impacts or other stresses around the same time. A new study provides some compelling evidence that one and only one impact caused the mass extinction, according to a University of Missouri Columbia researcher. So, one big kaboom is what they're now saying is what caused all the dinosaurs to die. Now, we're not as big nor as robust as the dinosaurs. So the next time you hear some scientist pleading for money to study near-Earth passing objects, and we've only got, some small percentage of them documented For God's sakes, urge your local legislators, your state and federal legislators, to give them the money. Because eventually something is going to come along, some big several mile in diameter type rock is going to come along, and they're not going to see it. It's going to come out of the sun, where it's going to be very hard to see. And, well, the dinosaurs, as I mentioned, they were big, they were robust, but they died very quickly. How do you think we would do? Next time some scientist has his hand out for money to look for something like that, for God's sakes, give it to him. I'm Art Bell. Hey, we're about to go to open lines, but let me read a couple of these. I appreciate all of the positive fast blasts that I get, certainly, but in a lot of ways, the negative ones are more interesting to read. Here we have College Station, Texas, and Heinrich, who says, "Hey, Art, with how much you and George saturate your show with apocalyptic content, it almost makes me think you want the world to end. Lighten up." Well, I'm not making these up. I'm just reading them. Now, want the world to end? I have a child on the way. Do I want the world to end? Hell no. Of course I don't want the world to end, but I do feel it might be important to call this sort of thing to people's attention. You know, small matters like the ocean having no more fish by 2048, that sort of thing. Global warming, viruses getting out of control, the kinds of things that would make life not comfortable for my child nor yours. So I think it's important that's what this show deals with, is edgy kind of stuff. If you want to really call it that, fine. And then there's this from Ray in Bellevue, Nebraska. I've never heard it rationalized quite this way, but he says, now, Art, if all the fish die, that's going to help with your so-called rising sea level, isn't it? This because the weight of all these fish is going to be gone and the sea level will lower. So we'll be better off. Also, there's absolutely no correlation between the weather in Florida or the East Coast and Philippine weather. You're off the deep end again. Well, Ray, actually, yes, there is. The world's weather is pretty much tied up together, and that the East Coast has had a light year for hurricanes and the Pacific a very heavy year for typhoons would indicate to me that the following year things will reverse, and it will be the East Coast of the U.S. that has a tough time with the big Category 5 plus hurricanes. That's just the way I feel, Ray. And then as far as all the fish dying, helping the sea level rise situation, I don't think, Ray, that all the fish dying is going to be a positive thing for us, even if it causes the sea level to rise not quite so high. Ray, I don't quite follow your rationalization, but if it makes you feel better, Ray, that's fine. By the way, the one very annoying thing here in the condo in Manila has been these little, we have these little tiny fruit flies, and they're simply impossible to get rid of, or I thought they were. And the building has tried all kinds of pest control companies, in fact, companies that do the biggest, best luxury hotels in the world, you know, that we've had them in. Nothing works. Well, the other day I happened to be in a Japanese restaurant, and I noticed they had this bug zapper. Now, it had two long bulbs in it, kind of ultraviolet purplish colored bulbs. And then behind, or just in front of the bulbs, there's this little grid, this electrical grid that is then protected in the front so nothing else can touch it. And every now and then you hear zzz, zzz. And so I thought, aha, that's the solution. Went straight to Ace Hardware. Yes, we have Ace Hardware here. And bought one. Brought it home. Put it up on top of the refrigerator, and voila, I haven't seen one of those little bugs in a week. Not in a week, and they were driving me nuts. Just these little teeny-weeny things. And now I'll be sitting in the living room, and every now and then I'll hear, zzz, and I'll smile. Another bug bites the dust. And so that has cured the entire problem. All right, let's go to the lines and see what awaits. First-time caller line would be Jamie in Calgary. You're on the air. Hi.
Hello, Art. How are you?
I'm quite well, sir.
That's good. I've been listening to you for a long time, and I'm really happy to talk to you. I was just kind of had some statements, questions. I've been looking into this. Kind of hit me last month. I was just surfing the internet. I ended up coming across this, what you'd call a documentary on 9/11, and
Okay.
was about, well, it was called Loose Change. I don't know if you've heard of it, but
I've not. Well, actually, I have heard the title somewhere, but go ahead.
Okay. Well, it was really compelling to me that I just never really looked at this before. But, I mean, there was some crazy things in there that just made me think, and
Think about what?
Well,
what did you think about?
I just think that those towers were they had explosives in the building.
Really?
I mean, if you...
I could swear I saw those airplanes plow right into the building with my own eyes.
Well, the airplanes did plow into the building. Now, that's another story. I don't know exactly how those came to be. You know, they say it was the terrorists in the planes that did it. That's another issue. However, the planes going into the building, if you look at the actual World Trade Center towers, they're 110 stories. They were built like, they had 47 steel columns running down the middle part of the building, and the outside kind of held the floors together with the others, those parts of steel. But anyway, what the planes did was they came in. The government said that the jet fuel melted the steel that held the floors up, so they collapsed in a pancake fashion, right?
That's right, yes.
So that's what they said. But if you actually take it, you know, you can't. They don't even account for the middle 47 steel columns that were in some parts of the building 4 inches thick steel. You know, you can't. Steel doesn't, like, jet fuel can't melt steel.
Oh, yes,
it's not hot enough.
No, yes, it certainly is. Actually, you watched a documentary trying to prove a point that something else was at work here. I don't buy into it. I've never bought into it. We've had any number of experts on who have said that indeed the jet fuel did get hot enough to do the job, and I'm simply not one of those people who believes, and nor will I ever believe unless I'm confronted with evidence that truly is compelling, and I have not yet. And believe me, I've looked into this and all the other documentaries. I'm sorry, I don't buy into it. Sometimes what appears to have happened is exactly what happened. Those were very large jetliners. They crashed into those buildings. There are some questions about Building 7. However, what happened there was a large geologic event. When those buildings came down, it is entirely possible that it weakened 7 enough so it came down as well. 7 is much more of a question in my mind than the 2 World Trade Center buildings. What happened to those, I think, is absolutely obvious. I think the temperatures were more than sufficient to do what was done. And once you have the pancaking, collapsing weight of the building down upon itself, well, down she comes. So, no, I don't buy it. I'm not one of those conspiratorial folks who thinks that our own government brought these buildings down, crashed an airplane into the Pentagon, and all the rest of it. I don't for one second think that. I think it's exactly what it appears to be. It was horrible, and I don't think we have to reach out for other explanations beyond the obvious. That doesn't mean that I'm blind to looking at possibilities. I'm not. I've looked very carefully. First-time caller line, you're on the air. Hi. No, make that wild card line. Russ.
Hi, Art. How you doing?
I'm okay.
Well, I know you're doing fine. Everybody asked you that. I heard a couple of weeks ago that you said you were trying to stop smoking.
Yes.
Okay. Well, when I had the flu, I realized that I went from 2 packs of cigarettes a day to nothing. Mm-hmm. And I'm laying in bed and I'm going, why am I not craving a cigarette? And I'm thinking there must be some type of a chemical reaction going on in my body. So I said to myself over and over, I want you to remember the chemical reaction that's going on in my body right now. Well, Art, it's been 8 years now, and I haven't smoked.
Congratulations.
Yeah. Now, I realized that.
I had the flu too, buddy. When I came over here, you can't take an international plane flight like this without coming. And I had a bad case of the flu, and then several colds. And I still crave cigarettes. So I'm sorry it didn't work for me. I'm glad it worked for you.
Well, did you have the flu though? I mean, I know you said you were sick.
Oh, I had the flu.
Had the full-blown flu?
Oh yeah, I had a temperature for days and days. Yes, I had the flu.
Wow. Jeez.
So it different things. We're all physiologically different people, and different things work for different people. And if that worked for you, God bless you. I'm down to, for example, yesterday during the program, I only smoked 4 cigarettes. Normally during the course of a 4-hour program, I would consume a pack of cigarettes. So I'm doing very well, and actually that accounted for over half of the totality of the cigarettes I even smoked yesterday. So I smoked about 6 cigarettes yesterday, and normally smoke about 4. So I'm I'm doing very well. I'm on the edge of running out of nicotine gum, and I don't know what will happen when I run out of gum. But I'm doing very well.
Well, that's good. I'm glad to hear. I was hoping that this would help you out.
This is, well, I'm not sure getting. No, I still smoked when I had the flu. How's that for awful, huh?
That's terrible. Yeah, I don't see how you could even crave it, because I was totally shocked I wasn't craving at all.
I'm told that the nicotine habit is 3 or 4 times more potent than the heroin habit, which must make it one of the most addicting substances in the entire world. Remember that day when all the cigarette presidents, company presidents sat there, CEOs, and said, one by one, no, it's not addictive. Not addictive. Right. Our cigarettes are not addictive. Yeah. Bull stuff.
Yeah.
I appreciate the call, sir. When I had the flu, I still wanted to smoke. Now, I did, during the flu and during colds, recognize the damage that cigarettes were doing. Because, of course, when you have the flu or a cold, you have additional lung problems, and so it exacerbates the problem anyway. So I'm well on my way. I'm doing pretty well, but I guess what I'm doing is trading the addiction of cigarette smoking for the addiction of chewing nicotine gum. And I'm getting concerned. They don't seem to sell nicotine gum here. I've tried, and I will continue trying to locate it, but I haven't found it yet. Wildcard line 2, you're on the air. Hi.
Art?
Yes, Scott
in
Michigan.
Hey, this is Scott, calling from Merrill, Michigan.
Yes, sir.
In our local newspaper on Sunday here, we had an article in here about an emergency signal that actually came out of Denver, Colorado, from a secretive Air Force facility in Colorado Springs, that when they tested it out, it actually jammed over 5 million garage doors.
Huh. I've heard of a number of cases of satellites and other types of signals that have accidentally jammed or opened and then closed garage doors, that kind of thing. So I've heard of this before.
Today, and that's the first time I've ever heard about it, so I just wondered if you know anything new or heard anything else that was going on.
No, it was an emergency signal, huh?
Yeah, it's supposed to be for the Homeland Security in case of a security threat.
I see.
So I don't know what they're trying to do or anything like that.
So they weren't actually trying to open or close garage doors?
No, it just said when they tested out the signal that over 50... I'm sorry. It says in the article over 50 million garage door openers and hundreds of residents found that theirs suddenly had stopped working.
Stopped working. That's interesting. I'm not sure. I could see that a signal like that might open or close a garage door, but I'm not sure what could jam a garage door. That's That's intriguing. 50 million of them at that. I'll have to look into that. Fascinating. Those frequencies that open and close garage doors are generally in the VHF range, occasionally in the UHF range. For example, the garage door that we had at KNYE Radio, was in the VHF range. And the signal, of course, from KNYE was so strong that it completely swamped the garage door opener. And in order to get it to work properly, I had to exchange the unit for one that worked on a UHF frequency and then add a little outside antenna on top of that and put a lot of RF protection on it and finally got it to operate properly, but it was quite a job. Okay, let's move east of the Rockies to Jeff, I believe, in St. Louis, where probably it's cold. How you doing, Jeff?
Oh, yes, definitely cold. Single digits. Good thing we got our power back a day ago.
Single digits?
That's what they're expecting. I'm on the phone.
Probably about 90 degrees here right now, Jeff, and about 90% humidity.
Oh, yes, definitely. Did you get my email? I sent you pictures and a video link of some of the damage.
No, I haven't received it yet. And speaking of damage, we have photographs now on coasttocoastam.com of some of the typhoon damage over here. But yes, I've seen some of the photographs of some of the damage from the ice storm there. It was incredible.
Oh, yeah, definitely. Where's that global warming when you need it?
Well, actually, Jeff, this is part of global warming. Global warming it's going to produce extreme weather in both directions.
I was trying to make a joke there.
I see.
Thank you for taking my call.
You're very welcome, and take care, Jeff. Yes, well, global warming, a lot of people say that, some in jest because they really understand what I'm saying. Others really are quite serious about what they're saying. It's cold, so global warming is baloney. Well, no, global warming will produce weather extremes of all sorts, and that includes cold as well. We're simply going to get increasingly... I hear a cat scratching on the door. We're going to get increasingly extreme weather of all varieties. On the international line, Matt in Ontario, welcome to the program.
Thank you very much. I just have a quick question. The first time I heard your program, I was about 16 years old, and it was your interview with a gentleman named Red Elk.
Oh, yes.
And I was just wondering, like, whatever happened to him and the Mel's Hole situation, if you've ever heard anything back or just...
I'm very tempted to be doing an update on Mel's Hole. I've been sort of wavering back and forth. I actually know how to get hold of the individuals involved, so stand by. I might do an update on it.
Okay, because I was about 16 years old, and it was the first time I just flicked on the radio.
How old are you now?
I'm 20. I missed school that whole day, too. I was scared to death.
You really? Mel's Hole scared you?
Yeah, and, like, I heard the program with the thing came out, and it took away the guy's cancer, and...
Oh, yes. Yes, but I mean, it wasn't one of those things where Mel's Hole was going to get you. It was sort of a regional thing, close, to where it was happening.
Yeah, but it was so amazing, like, what was down there. Like, I was born in June. I'm a Gemini, and all these things. June 5th was my birthday.
Mm-hmm.
And
I'm June 17th, also a Gemini.
Mm-hmm. And life's weird. Like, I have a very weird dreams. Every night I have a dream. I'm always very lucid. I'm flying around. I'm doing very amazing things, and your program is really giving me insight, and I appreciate it.
Okay, buddy, take care, and who knows, maybe we will do a update on Mel's Hole. One of the things that has fascinated me all my life, along with time travel, which, by the way, at least in part, will be a subject coming up next with Sean Carroll. Time travel, that is to say. The other thing that has fascinated me all my life are deep holes. Any deep holes in the ground. There was a young lady named Kimberly who found one in Canada, and we're trying to do a follow-up on that. But if any of you know anything about very deep holes in the ground, know of one, a secret one perhaps near you somewhere, I want to know about it. Now, to get to me, you simply send me an email. I'm Art Bell at mindspring.com. That's ARTBELL, lowercase, at Mindspring, MINDSPRING.com. Love to hear from you on any subject. When we get back, Sean Carroll, and we'll be talking physics. Stay right where you are. You are. How you doing, everybody? Morning, afternoon, evening. About to launch into one of my favorite subjects, physics in general, and time travel, of course, being part of that. Sean Carroll is a senior research associate in physics at the California Institute of Technology. His research involves theoretical physics and astrophysics, focusing on issues in cosmology, field theory, and gravitation. His current research involves models of dark matter and dark energy, cosmological modifications of Einstein's general relativity, theory of relativity, the physics of inflationary cosmology, and the origin of time. He has received research grants from NASA, the Department of Energy, and the National Science Foundation, as well as fellowships from the Sloan and Packard Foundations. This is going to be a very, very interesting interview. So if you're one of those who wonders what more there is to all of us, you're going to want to stay right where you are. In a moment, Sean Carroll. Sean Carroll, welcome to the program.
Hi, Art.
Welcome. It's great to have you. I see that you apparently have some interest yourself in time. Is that correct?
Yeah, absolutely. It's one of the things we study, trying to understand how the universe works.
It's a passion of mine. What to a physicist, which you are, what does time mean? It's a wonderful first question. What does time mean?
Well, it's a loaded question because it means more than one thing. One of the things that we understand about time that we didn't used to is that there's more than one definition that works. So there's a sort of universal time that we think of as labeling places in the universe. If you want to meet somebody for coffee, you need to tell them what time you're going to meet them. Just like you have to give them a position, you also have to give them a time. But then there's also a personal time. There's the amount of time that you measure as elapsing if you pay attention to your wristwatch as you walk along. And in the old days, we used to think these were the same, but now we know better. They can be different from each other. And then finally, there's a sort of more familiar notion of time as something that flows, something that changes, something that passes us by, which physicists relate to entropy and thermodynamics, and that is something we understand parts of, and other parts still remain a mystery.
Is time a real thing, or is it our invention?
I think time is pretty real as concepts in physics get. What is really real is space-time, which is how Einstein taught us to describe the whole universe all at once. And time's a big part of that. Because you and I and all of our friends move slowly with respect to each other compared to the speed of light, we have a fairly uniform notion of what time is. But really what's out there, if you want to talk about what's real and what's not, what's real is space-time, the whole four-dimensional place where we live.
When we talk about space-time, do you mean, for example, how long it would take us to travel to Alpha Centauri at the speed of light?
Well, that's right. Those notions are closely related. What I mean, though, is really just the simple idea that we could have been talking about back long before Einstein, when Isaac Newton was our leading authority when it came to time, which is just that if, again, you want to meet somebody, if you want to specify some place in the universe, and you want to see somebody else there, you need to give them 4 numbers. You need to give them 3 numbers saying where they are in space. Let's say their latitude, longitude, and height above the ground. but you also need to tell them what time you're going to meet them there. Otherwise, you'll be there at the wrong moment, and they're not going to be there to see you. So it takes 4 numbers to specify a location in the universe, and those 4 numbers are what we call the 4 coordinates on space-time. So it's really just nothing more deeply complicated than that, just the fact that space and time are both parts of what makes up the universe. And then how space and time mix together to create space-time gets tied up with this question of what we would experience if we zoomed out to Alpha Centauri near the speed of light.
Okay, let me ask you this. Many listeners have asked me this, and I'm never quite sure how to answer it. If time travel were possible to go to the past or go to the future, and we had a machine to accomplish this, many listeners have called and said, well, look, the Earth is in orbit around the sun. The Earth is moving. So if we traveled in time, is there any chance that instead of ending up, in the same place on Earth, only at a different time, we would end up in a different time, all right, but perhaps out in the vacuum of space where Earth once was or will be or isn't?
Well, yeah, in fact, it's more than a possibility. It's practically a necessity. One of the things that we have to understand when we start talking about traveling through time is that traveling through time is something that we all do all the time, as it were. Namely, we move to the future at a rate of 1 minute per minute, whether we like it or not.
Yes.
And in space-time language, that means that you and I and everybody else describes a path, a trajectory through space-time, and that is continuous. We don't ever sort of poof out of existence in one place and poof into existence some other place, in space or in time. We're always having a smooth trajectory. Where we were right now is very closely connected to where we were a fraction of a second ago. Mm-hmm. So if you want to talk about traveling backwards in time, what it really means is traveling through space and having space be configured in such a nice way to allow us to do a loop so that we come back before we left. So if you build a real time machine, if it were possible, we don't know if it's possible or not, actually.
It would have to bend space, essentially.
Well, it would require 2 elements. One thing, you would need something that bent space and time together. You need a strong gravitational field.
Right.
To warp space and time to allow for travel backwards in time, or at least, to allow for travel that brought you to your own past. But then you would need to actually make that journey. So you need some object that made you travel through space, namely a rocket ship or something like that. So the crucial point is that you would not jump in the machine, the lights would flash, smoke would come out, and you would disappear to arrive at some other point. You would blast off in your rocket ship, and to you, time is moving forward 1 minute per minute. But then you go in your rocket ship in the right way, and eventually, 2 weeks later, you come back, and there you are, looking at yourself in the pad, ready to have that little rocket be launched.
Sorry, are you saying that...
What it would be like if it were possible.
You're saying then that you think time travel via the science fiction machine is not possible?
That's right. If time travel is possible, and I want to keep saying if, it would look like space travel. It would look like space travel under certain very specific circumstances. That's right.
Well, what about if we are able to create a black hole? Now, they're working on that little idea at CERN.
That's right.
Albeit a very tiny little one at the moment, but suppose they were able to create a substantial black hole, aside from the possible catastrophic results of doing such a thing. If we could create a black hole, then one would think that that could be incorporated into some sort of machine, which would allow you to get near its event horizon and zip from one time to another, essentially.
Well, it's related, but it's not the same thing. And so, in fact, if we made a black hole in the conventional way, if one can speak of such things, we waited for, we don't make black holes every day, but the universe makes black holes every day. Stars explode and collapse and form black holes. And what would happen if we stayed far outside and a friend of ours zoomed in close to the black hole but didn't enter, stayed there for a while and came back, is that if, from our point of view, much more time would have passed than from their point of view. So, if anything, A black hole is a machine that will take you into the future even faster. So if you turn it around and you zoom close to the event horizon and you hover there for a moment and you come back, to you only a day has passed, but to the rest of the world it's been 500 years.
Are we sure that black holes really do exist? Are we positive about that now?
We're pretty close to positive. We never get to be 100% positive in science at all, and certainly not in astronomy. Our theories predict that they exist. They make certain very firm predictions for how we should be able to perceive them in terms of X-rays coming out in the vicinity of black holes and so forth. And those predictions come true. We see things that look exactly like we think black holes should look. In fact, at the center of our galaxy, the center of the Milky Way galaxy, you can see movies that have been made by people taking pictures of the stars at the center of our galaxy over a course of years. And you see that these stars are not moving in straight lines. They're moving in orbits around something that is big and dark and not shining. And you can figure out from the distance to the center of the galaxy and so forth how much mass there must be in that big dark thing, and it's 1 million times the mass of the sun. The only thing we know that can be is a black hole.
So it must be there.
Either that or something even better.
Even better. What would you guess would be in the category of even better?
Well, what is certainly there, and certainly elsewhere in the universe in other examples, are very large concentrations of mass in very small regions of space. So according to general relativity, according to Einstein's theory of gravity, the only thing those can be are black holes. If they're not black holes, that means that Einstein was not right. And that means that gravity is described in some way that we don't yet understand, and therefore we would have to understand that to understand what these things are. And that's what physicists love, when you discover something out there in the universe that our current theories don't quite explain perfectly. But so far, I should say that our theories are explaining things quite well. Everything that we see in astrophysical situations near black hole candidates is quite consistent with what Einstein predicted.
So gravity, that which keeps our feet on the ground and so forth and so on, is mass.
Gravity is created by mass. What gravity is the curvature of space-time. So that's why gravity comes involved when you want to make a time machine, because gravity is a manifestation of the fact that space and time are not like Euclid thought they were, with triangles having 180-degree angles inside, et cetera, everything you learned in high school. But mass and other forms of energy actually warp space and time into each other.
So the Earth warps space and time.
Absolutely. Otherwise, we would all float away.
And creates the gravity that keeps our feet on the ground.
That's right.
And a black hole, of course, is it's so many million times stronger than the gravity produced by Earth. And a black hole is a collapsed star, correct?
Well, a collapsing star is the simplest way to make a black hole. The black hole at the center of our galaxy, which is 1 million times the mass of the sun, is started out as a collapsed star or some similarly catastrophic event, but then accreted a lot of the matter in its neighborhood and just grew and grew over the last few billion years into the size we see it today.
Is it going to be possible, in your opinion, to create at CERN, for example, a black hole, even a small black hole, even a very sort of temporary, very quick black hole? Is it going to be possible?
I would bet against it if you gave me odds. It's something that we all hope would be true because it would be so fascinating, we would learn a lot. And it's also certainly respectable as an idea to think about. It's one of the sort of more speculative theories that are taken seriously, but it definitely is taken seriously, and that's why you have to do the experiment, because you don't know ahead of time.
If we do the experiment and if we create a black hole, giving me a straight-on answer, is there any danger in doing that?
No.
Potential danger?
No, none at all.
Why?
Well, there's two reasons. There's the wimpy reason and there's the extremely strong reason. The wimpy reason is that everything that we understand or think to understand about black holes says that even if you make one, it will very quickly evaporate. It will just disappear. And now you might say, well, maybe we don't know what's going on, and that's true. On the other hand, The things that are going to be happening at the particle accelerator at CERN, so in Geneva, outside Geneva, CERN, the particle accelerator is going to be turning on next year, going to be reaching energies that we've never reached before in experiments here on Earth,
Right.
but have been reached many times elsewhere in the universe, all the time. You have protons and other particles colliding into each other elsewhere in the universe. Nothing dramatic happens. So we know that whatever happens might be interesting to us, but it's not going to be some cataclysm. And also, you should emphasize that black holes are, the important thing about a black hole is not that its gravity is strong, but that it's small. So if our sun, if all the mass of our sun tomorrow turned into a black hole, the Earth would not be sucked into it. The Earth would go along in its orbit exactly as it always has because we're far away. There's just no more or less gravity if you turn the sun into a black hole than it already has.
Well, all right, let me give you something to potentially worry about.
Okay.
So a black hole could be potentially very small and very powerful, right?
Powerful on microscopic scales. It really would not be that powerful. If a black hole that size went by your nose right now, you would never notice.
Uh-huh. So
we're talking about something, it's powerful by microscopic standards, but the black holes you'd be creating are less than a trillionth of a gram in mass.
You're talking about the ones that CERN might make.
CERN, yeah.
Okay.
Yeah.
But here's my question. We all know about the massive black holes that astronomers think they have identified. Could there be a scale of black holes? In other words, could there be a black hole, I don't know, a tenth the size of our Earth, for example? Could there be varying black holes, a smaller, relatively smaller black hole? And is it possible that these black holes are not in absolutely fixed orbits? In other words, could there be marauding black holes?
That's a good question, and part of me wants to say it's certainly possible. It is certainly possible if you don't tell me how many of them there are. It's certainly possible that in our galaxy there's a handful of black holes the mass of the Earth going through. And, how would we know? We would never know. It wouldn't be any different, as far as we're concerned, from a bunch of planets the size of the Earth going around. Because, like I said,
unless one ran... Well, I guess what I'm asking is, if one of these marauding black holes, should they exist, were to collide with the Earth or another planet similar in size to ours,
right?
What would the result of that be?
It would be a mess. However, you said, could these things exist? And I said yes, but the number of these things is going to be much less than the number of good old-fashioned planet-sized things, planet-sized planets in the galaxy and in the universe. And if another Earth-sized planet ran into us, it would be equally, if not more, disastrous to the Earth.
Really?
And that's not very likely. So these are not in my top 10 list of things to worry about over the next 100 years.
Okay. From time to time, we see these incredible, I'm a sun watcher. I'm a ham radio operator, have been all my life, since I've been 13 years old. And so I watch the sun very carefully. And occasionally we've been getting these incredible gamma bursts that just come from not our sun, but apparently seem to come from deep space. Now, I don't know what causes these giant gamma ray bursts, but they certainly affect radio transmission. And they are real, and they're where are they coming from? And is it possible that you could get a gamma ray burst that would be so strong, so big, that it would be damaging to life on Earth?
Well, I have to make a parenthetical comment here. There are gamma ray bursts that astrophysicists are fascinated by that exist throughout the universe. We've been studying very much for the last 20 years. I can't imagine that they affect radio signals here on Earth very much. They're extremely powerful if you're close by, but they're so far away that we need to strain with our best telescopes just to notice them at all. However, like you imply, if one happened nearby, it would be lights out for us, depending on how nearby was. What we're thinking in terms of these gamma ray bursts is something like a supernova or something like two black holes
Yes.
coalescing with each other by giving off gravitational radiation and then unleashing a huge explosion of energy. So we could have one of these elsewhere in our galaxy and we'd be okay. It would be quite the show in the sky, but there wouldn't be any noticeable effect on our lives. But if one happened, as close as the nearest star, that would be something else.
All right. Hold it right there. Sean Carroll is my guest. Physics, the subject, time travel, sort of interwoven into all of this, but we'll go all over the place. From Manila in the Philippines, I'm Art Bell. Actually, that's very well sung. Time keeps flowing like a river to the sea. My guest, Sean Carroll, is a research associate in physics at the California Institute of Technology. His research revolving around theoretical physics and astrophysics, focusing on issues in cosmology, field theory, and gravitation. Just the right fellow to be talking about exactly what we're discussing. Back to Sean Carroll in a moment. So then, Dr. Carroll, I didn't say anything about that. I figured it had to be doctor. It is doctor. Welcome back. Doctor, so a time machine is impossible with what we know, the known laws of physics. But how about this? There's this new quantum thing that I've been trying to get my head, and a lot of other people have, wrapped around for a long time. This quantum world where apparently a particle here and a particle there in North America where you are can interact at exactly the same time. Now, Einstein said something about, I'm paraphrasing here, goofy interaction at a distance. He didn't like it. He understood it.
He called it spooky.
Spooky, yeah, that's it. Spooky interaction at a distance. He didn't like it because it didn't fit in, and it does indeed seem to violate everything. In other words, it wouldn't matter whether these two particles were Philippines to North America or North America to Alpha Centauri, they would interact at the same time. Now, that necessitates communication. You just simply can't have a coordinated movement without a communication occurring. Maybe at some level that we don't possibly understand yet, but it exceeds the speed of light. However it's happening, it's bending all the rules, which I guess explains why he didn't like it, because he loves rules. Rules.
Well, okay, there's a couple things. One is that, the good news is that your first statement, that according to the current laws of physics, time travel is impossible, is actually a bit too strong. I think, according to the current laws of physics, it's an open question. It might not be possible, but we can get into the details of that without worrying about spooky quantum mechanics, if you like. But as far as the spooky entanglements are concerned, I really think that we're simply being misled by the fact that the English language and all the other languages in the world were not developed in order to talk about quantum mechanics. And we're being misled by words, even though what's going on is not that spooky at all. In particular, the phenomenon of entanglement of two particles that are separated by large distances doesn't violate any rules at all, but it makes us nervous. But making us nervous is not one of the laws of physics.
Well, no, wait a minute. That's
make us nervous.
Getting nervous does not properly explain. There has to be a communication. There has to be.
See, that's the thing.
Tell me how there doesn't.
Well, here's the point. I have a particle here in Los Angeles, and you have a particle there in the Philippines. And the rules are that if you ask me, is this particle spinning clockwise or counterclockwise, I cannot give you an answer. I just don't know until I observe it. And likewise for your particle over there. However, there's another rule that says if I do observe my particle, and I find that it is going clockwise, then I can predict with 100% certainty that yours will be going counterclockwise. Okay? But so what? how do I possibly use that to send a signal to you? I mean, if I observe my particle and I decide that it's clockwise, then I know for a fact that yours is counterclockwise, but I can't do anything with it. There's nothing that helps me send a signal to you. So it makes us nervous, but there's no possible way that I can use it to send information faster than the speed of light.
Yet.
Ever.
Ever?
You can prove a theorem, actually, yes. All of this spookiness is, Einstein wrote a paper about this, a famous paper, Einstein, Podolsky, and Rosen, and the point of his paper was, look, here is the prediction of quantum mechanics according to its rules, and I don't like it. It makes me nervous. Therefore, there must be something missing. So we've moved a little bit beyond that now, and we've looked at this a lot, and we've thought about it. We've done the experiment, and it's true. And we realize, here is the prediction of quantum mechanics, and it's true, and we have to learn to deal with it, because that's what nature is like. And nevertheless, one of the rules that it is obeying says that we can't send information faster than the speed of light. It's perfectly consistent with that rule.
I don't understand that. The two particles have to be communicating to, in other words, a movement of one sort. They can actually manipulate these particles. Is that correct?
Well, yeah, that's right. I mean, like
Okay.
I said, they've done the experiment, but you need to tell me how I can possibly make use of the fact that if my particle is going clockwise, yours is going counterclockwise.
I can't. I'm not the guest.
Yeah. Well, then, if I can appeal to authority.
It is not sufficient to say that, in my opinion, that, okay, it happens, and we just have to learn to deal with it. It's our job to understand why it happens. It seems like there has to be a communication. I'm not trying to be rude here. It just how can one do a flip and the other do a flop without the flopper knowing there's been a flip?
Well, that's because we're used to thinking in, like I said, classical terms. Classical is what we called the laws of physics before quantum mechanics came along. According to classical mechanics, there would be no way for this entanglement to exist over a long way. But this whole story that we're telling of me looking at my particle and seeing it going clockwise, and then instantaneously your particle is counterclockwise, that's the part that is a bit of a fake. That's the part that our language is letting us down. Because what I said, when I was very careful, I didn't say that instantaneously when I observed my particle, your particle was going counterclockwise. I said that now I knew with 100% certainty that if you observed yours, you would see it to be going counterclockwise. So there is no need for a signal to travel. There's a consistent history of the world in which I observe my particle, you observe your particle, and the laws of quantum mechanics tell us that tomorrow, when one of us flies across the ocean to visit and we exchange notes, we realize that one of our particles was going clockwise and the other was going counterclockwise, and it's completely useless in terms of sending a signal.
Right now. But you will say it will always be so.
According to the rules as we understand them right now. So, I mean, I'm always, there's two different things that we do in physics. One is take the laws of physics as we understand them and tell you what they predict. But the other is wonder if those laws are correct and wonder if we can move beyond them. According to the laws as we understand them right now, the same laws that predicted this crazy phenomenon, you cannot use this crazy phenomenon to send information faster than the speed of light.
Okay, I guess. It still seems like there has to be a communication that is occurring at what exceeds the speed of light, virtually instantaneously. This is happening now. There's an entanglement. Can you explain to me the manner of entanglement that causes this to happen?
Well, what I would say is that you can tell the story without ever using the idea of instantaneous change across very large distances. So the story is that if you and I both observe our particles and then later we meet up and we ask each other what happened, we will never both be saying that we observed our particles to be going counterclockwise. One of us will get one answer, the other will get the other answer. And then you can say, well, how could that happen? What must have gone past? And I can just say, look, the rules don't say that a little signal had to go from one particle to the other. The rules just say that every time we get together, we will agree that our two particles were spinning in opposite directions.
Okay. Trouble with words. Then what does define entanglement in the quantum world for me?
Well, what entanglement means is that if I have a little system right here in front of me that I'm holding in my hand, according to good old classical mechanics, before quantum mechanics came along, if I knew everything that was going on in that system all by itself, and I didn't bother it, I didn't do anything to it, I could predict what would happen at any future time with that system. But entanglement says that systems are not local. Systems are not described as existing just isolated in some point in space. I can have a system that somehow isn't fully described right here in front of me unless I include its relationship to things very, very far away. Which is fun, arguably spooky, but does not let you send signals faster than the speed of light.
Okay. And in your opinion, never will. It's just weird.
That's right. And, it's not, I don't want to dismiss worrying about it, because Einstein worried about it, and Einstein was a smart cookie. But we have, since Einstein, sort of learned to understand the consequences of it better, and we've learned to draw sharper distinctions between a set of words that makes it sound as if something is happening instantaneously and the actual thing that is not allowed, which is sending a signal that could be used to carry information faster than the speed of light. And quantum mechanics allows us to use words as if things were happening instantaneously, but it does not allow us to send information faster than the speed of light.
Okay, but this entanglement is happening faster than the speed of light, yes?
Well, this entanglement exists all over the place. And then we come up with a set of words to describe what will happen if we observe part of the entangled system.
Boy, is this confusing.
Well, I hope so. A lot of smart people bounded their head against the walls for decades trying to figure it out. I hate to say it, but it kind of becomes easier if you can write down some equations. I know that's a completely unhelpful answer, but we're used to things happening locally. We're used to, if I smack my hand on the desk, sound waves come out from that desk and they move at some speed, and it all makes perfect sense to us. Quantum mechanics doesn't quite obey those rules. It really says that the state of me here in this room might be entangled, intertwined in some important way with the state of something very, very far away in the universe.
Indeed so.
Interesting and fascinating, and I do not want to downgrade the amazingness of that statement, but I do want to point out that you can nevertheless show, using the equations, that you can't use that amazingness to send information faster than the speed of light.
All right. If we develop quantum mechanics, what uses can you imagine as we develop as we understand more about this spooky thing?
Well, one of the most exciting, plausible technological developments is what we call quantum computing.
Yes.
So if I have my little particle that is either going clockwise or counterclockwise, in classical mechanics it really is either going clockwise or counterclockwise, but in quantum mechanics it's doing neither. It's described by a probability that it's doing one thing versus the other thing, all at once. So that one little spinning particle has a lot more information in it. Instead of being either clockwise or counterclockwise, it has 55% being clockwise, 45% being counterclockwise. So that's a lot more information. And if you then take 20 such particles and they're entangled, what that means is that to describe the entire configuration of 20 particles, you need to tell me what is the probability that particle 1 is doing something if particles 2 through 20 are doing something. And it's a tremendous amount of information required just to say what that is. And what that means basically is that instead of a complicated hard disk to have, gigabytes of information on it, you need a couple particles. And by doing manipulations on those particles, you can do incredibly complicated calculations, quantum mechanically, enormously faster, unimaginably faster than you could do them on a classical computer. And that's an exciting technological development. That's going to be the next quantum leap, if you'll excuse the phrase, in how computers work. They'll be just enormously more powerful once we harness that possibility.
I wonder how a quantum computer developed would compare to the human brain.
The human brain, as amazing as it is relentlessly classical. It does not, as far as anyone knows, and this is, I guess, a tiny bit uncertain, but I think that there's no reason to think that the human brain takes advantage of quantum mechanical possibilities. Quantum mechanics, even though it's amazing, is also a little bit delicate. If you tend to take this, one of these systems of two particles far away that are entangled with each other and bump into one of them by accident, it all collapses and the entanglement goes away. Yes. Our brains are being bumped into all the time, so they remain sort of pure and unentangled. So as far as anyone knows, the human brain just takes advantage of the fact that it's a complicated but relatively mundane system of neurons hooked up together in a very highly interconnected way.
So, Doctor, then you're probably saying that a quantum computer would make a human brain look like an abacus.
Well, it's not a very good comparison, right? I mean, my calculator wristwatch makes me look kind of stupid if you're trying to multiply two 5-digit numbers together, right?
Yeah, that's right.
But if I'm trying to cook a nice meal, I will win. So all of these comparisons of raw computing power to the human brain are a little bit misleading. It's not the hardware that is the trick; it's the software.
Yes, indeed, the software. One of the holy grails, of course, of computers is eventually AI. In other words, some sort of artificial intelligence.
Yes.
How would you say that moment of artificial intelligence would actually be measured? When would we know that we have achieved something beyond just a faster computer with more storage? Something that, knows that it exists?
This is a great question. I'm going to wimp out and say I have no idea how we would answer that precise question. But I will go so far as to say that when something like that happens, when computer power advances to the point where we're beginning to talk about true artificial intelligence, the kind of intelligence we will get will look very different than human intelligence. Not just that it'll have different wants and needs and feelings of justice and beauty, but that it will be really good at some things and really not so good at other things. The human brain is not something that a set of engineers wrote up a little code to make. It's the result of billions of years of evolution of neurochemical processes, et cetera, et cetera. And it's specialized for certain tasks, and we don't yet know how to encode, how to reproduce those specialties. So we might get a computer that is very good at playing chess or playing poker and not very good at frying eggs, or the other way around. So I think we should be surprised. We will be surprised at what computers can do well quickly and what computers nevertheless remain very dumb at doing as the future progresses.
How do you feel about the possibility of humans increasingly being entangled with computers? In other words, boy, we're beginning to get people who are actually connecting their nerve endings to computers in albeit very, I suppose early and raw ways, but it's leading to a world, not too many years down the line, where we're going to be kind of part human, part machine if we wish it.
Well, it's absolutely true. I mean, the first steps are very clear with simple things like pacemakers and artificial limbs, right? And this is just one of those areas, I have to confess, that nobody has ever correctly predicted what the future will look like, even 50 years down the line, much less 100 or 1,000. 100 years ago, I think the correct thing to think of when you're trying to answer these questions is what people would have said 100 years ago if you asked them the same question. And they would have said, what, a computer? What is that? And so 100 years from now, we're not going to be talking about human beings interfacing with computers. There'll be some other entirely new concept that is analogous to a computer, but is, we're not even dreaming of right now, that everyone will be wondering, how will that change how human beings live? So I'm very, fascinated and excited by the possibilities, but I'm completely pessimistic about my own or anybody else's ability to predict what will happen next.
Mm-hmm. How do you feel about the future of the human race? Now, I've frequently interviewed other theoretical physicists who are, when you really pin them down, awfully pessimistic about the possibility of our evolving past, Michio Kaku, for example, says past a Type 0 planet, which he says we are right now, to a Type 1 planet. He feels that we will ultimately blow ourselves to smithereens. We'll tackle that one when we get back from the break, which we're right on top of right now. I just looked up and poof, all that time is gone. Dr. Sean Carroll is my guest. I'm Art Bell from Manila, the Philippines. Dr. Sean Carroll is my guest, and he's obviously a heavyweight in the world of physics. He is a senior research associate in physics at the California Institute of Technology. His research involving theoretical physics and astrophysics, focusing on issues in cosmology, field theory, and gravitation, all the things that would be involved, possibly, in time travel. In a moment, we'll talk to him about, we'll find out how much of an optimist or a pessimist he really is for all of mankind. There are some positive signs, but there are an awful lot of negative signs out there right now for us. So in a moment, we'll probe that area. Once again, Dr. Sean Carroll. Dr. Carroll, I interviewed a number of theoretical physicists, and one of them, Dr. Michio Kaku, feels that, he does a kind of a Star Trek explanation for where we are in the world, with a Type 0 planet, Type 1, Type 2, Type 3, Type 3 being able to control the power of suns, and, that's a long way away. But he said we're a Type 0 on the verge of becoming a Type 1. And when you really pin him down and ask him whether he feels we can survive the discovery and development of Element 92, he really says no. Our chances of moving on ahead are just tiny. And I wonder if you feel the same pessimism.
Well, I think this is one of those things where literally everyone is entitled to their opinion, since we have no information whatsoever. We have no data about what happens to a civilization when it gets to our point in development. But physicists, if you're thinking that they seem pessimistic, are probably so because they've all heard of the Fermi paradox, the basic problem that if a civilization does last for a while, it doesn't take it that long, astronomically speaking, for it to fill the entire galaxy. And it wouldn't be hard for humanity to have noticed other civilizations back when we first started pointing radio telescopes at the rest of the galaxy. But they're not there. There's no civilizations out there, even though they should be very easy to spot.
Very troubling.
It's very troubling, and it might be, there's two very, very obvious explanations. One is that, despite what you might think, it's very hard for life ever to develop. Even though there's lots of planets, that maybe that the particular set of things that led to the first microbe here on Earth were just less likely than you think, and that we are in fact unique, at least as far as our own galaxy is concerned.
Life is rare.
Yeah,
that's certainly possible. Do you buy into that one?
I have no idea. No one generally accuses theoretical cosmologists of humility, but on that one I'm going to be humble. I think that I have no idea.
Okay.
And the other possibility is that life happens all the time and civilizations develop and they destroy themselves. Also very possible. Once we get to be powerful in a certain sense of the word, we turn on all sorts of ways to destroy our own planet that we didn't have back when we were hunters and gatherers. I think that global warming and global climate change is something that is potentially disastrous, that we don't know what's going on, and who knows? It could, 100 years from now, 200 years from now, make things really sort of disastrously bad for us.
Oh, yes.
So I have no idea.
Have you looked at the North Pole? I mean, my God, if you look at pictures of the North Pole 40 years ago, pictures today, if it doesn't scare you, then you're just not an observer. I mean, 50% of it is just gone. We're going to be navigating ships where the ice used to be, and the Ross Ice Shelf down south may be getting unstable. I read stories about all the fish in the ocean being dead by 2048. These are stories that are really, really scary, and they're not science fiction. They're real, and it all seems to be speeding up. So even if we don't blow ourselves up, it seems entirely possible that we'll simply make it unlivable.
It is possible, yeah. And again, I want to stress that I don't know, but I can look at the graphs of the amount of carbon dioxide in the atmosphere as a function of time, and you see it sort of jiggling along very, very, it goes up and down, but there's a central value that doesn't ever stray very far from until the last 50 years, where it's gone zoom, way up there. And you can say, and there are people who say, well, we don't know whether that's good or bad, what will happen. And that's true. And, it's also true that if you take a giant needle with some unknown chemical in it and stick it into your brain, it might make you smarter. You never know. But you wouldn't want to do that experiment if you didn't actually know what was going to happen. You should be careful a little bit and a little conservative to allow the conditions under which you can exist to continue on for a little bit.
Yes.
So I know that, I know physicist friends who are very highly trained about this, and even though what they really want to do is to tell NASA to help them build their favorite satellite or whatever, they're saying, hello, guys, you really should be paying attention to what's happening to the Earth, because that's what everyone will be talking about and nothing else 50 years from now.
Well, with what we know about physics, if we screw up the Earth, there are many who say that we had better figure out a way to colonize other planets if we wish mankind to continue. But, gee, with what we know about physics, the nearby planets we have in our system, they don't seem all that particularly hospitable at the moment, unless we're able to somehow terraform them. And getting to another star system, well, that just doesn't seem possible with these damn laws of physics.
Yeah, I think that if you're thinking about what can go on, if you're thinking about what might happen if we destroy the Earth, it depends on what you mean by destroying the Earth. If we really do have some sort of nuclear war, I actually personally don't think that would destroy the Earth and kill all the human beings. It would be a terrible disaster and a cataclysm, but humanity would probably survive. And if you're talking about global climate change, then it's a different thing, but it still remains true that living in Antarctica or living in the bottom of the ocean is a more hospitable environment than living on the moon or living on Mars. So it's nice to contemplate visiting other planets and colonizing them, but it's not a practical suggestion in terms of extending our lifespan in the foreseeable future.
No. And since the closer-in planets are not hospitable, what I said about getting to another star system is sadly true, isn't it? In other words...
Well, it takes a long time. It's not that you can't do it. To get to the nearest star requires 4 years if you travel very close to the speed of light. So
which we can't.
Which we can't right now, but that's an engineering problem. Someday we will be able to build rockets or the successors of rockets that can go close to the speed of light. The laws of physics say nothing about that. They allow you to do that, so someday we will, unless we kill ourselves first.
So we could, without biological difficulty for man, we could travel close to the speed of light. There's no law that says we would begin to get sick or something awful would happen to us as we approach the speed of light?
That's right. Yeah, no law against that at all. In fact, if we don't kill ourselves, if humanity lasts another 10,000 years, I'd be much more surprised if we hadn't sent spaceships to other star systems than if we had.
So then if life is fairly common, which, in my way of thinking, when you look up at the night sky and see all those stars, and, we've now discovered lots of planets around stars, the bigger ones anyway, so you can imagine the small ones must be there. There must be other fairly habitable planets out there, and yet SETI looks and looks, and no signals yet. No hint of anybody anywhere yet. That's very, very concerning.
Well, I don't know if it's concerning or not, but it's certainly true, and it's information. It's giving us a little bit of data when we try to answer this question, how common is both life and advanced civilized life on other planets. And the thing is that there are a large number, very, very probably there are a very large number of star systems with planets in the observable universe, and probably most of them don't have life on them. So if you want to know the total number that do, you have to take the very large number of planets and multiply them by the very small number, which is the percentage that have some sort of life. And the answer is we have no idea what the answer to that is right now.
Well, except that we have no hard evidence that we've been visited. We certainly have no evidence that we've received a signal yet, despite our best efforts.
That's right.
Should we be working? Yeah, should we be working harder at that? In your opinion, we have. SETI is now basically only a privately funded effort. Should it be getting a lot more attention? Be receiving more funds?
Well, I think actually it gets about the right amount. I'm not an expert, so I don't know exactly how many it gets, but it's a very high risk, very high gain sort of proposition. Very high risk in the sense that the chances per year that you're going to succeed and find something are very, very small, but obviously the consequences of finding something would be tremendous. So it's absolutely worth doing, but it's not worth making a priority when there's plenty of other things we could be doing whose payoff is a little bit more tangible and guaranteed.
Do you think that where the Earth is headed right now with global warming can be turned around? I'm beginning to hear some scientists suggest that it's already too late, that even if we were to begin turning things around now, which seems improbable, that is to say that we could do it, as you look around the world, the U.S. has certainly taken some steps, but gosh, I'm here in Southeast Asia, and I can tell you what's going on in China would just scare the tar out of you in terms of what's being put into the air, that sort of thing.
Yeah, I have no idea whether or not we can reverse it, but that question is a tiny bit academic since we're not trying very hard to even slow it down, much less reverse it. Right. So my focus personally, and again, this is not my area of expertise, but as a human being and a citizen, my focus is taking seriously the fact that we can't just keep dumping pollutants into the air without any regard for the consequences. So cutting down on carbon dioxide emissions is the first step. Forgetting about whether or not we can fix it, we should stop, shocking the system that we don't understand so dramatically.
Indeed. All right. Maybe you seem to be very good at this, so let's try with dark matter. I still do not properly understand at all what dark matter is and dark energy. I really don't understand what they are.
Oh, that's easy.
It is?
Yeah, it's, the simple version of dark matter is just matter, particles, just like atoms make up you and me. There's some other kind of particle, something that is not a proton or a neutron or electron or any other kind of particle you've ever seen in the lab, but there's some kind of particle that has a mass, and there are a lot of them out there in the universe. And the thing about these particles, these dark matter particles, is that they don't bump into ordinary particles directly. If you had dark matter particles going through your body right now, you would never know, because you probably do have those dark matter particles going through your body, and you don't know. However, the accumulated effect of all these particles gives rise to gravity. One of the things that Einstein told us was that anything that has mass creates a gravitational field.
Right.
And so even though these particles don't bump into our detectors directly, we can measure the total gravitational fields in different parts of the universe, and we can look at the ordinary matter, the stuff we know is there, and say what gravitational field would that produce And over and over and over again, it falls dramatically short.
So there's gravity coming from somewhere that we don't understand.
That's right.
And that leads us to say, well, it has to be dark matter, this stuff we call dark matter. I don't understand if it has mass in a way we can measure because of the gravity, then how can it not bump into conventional matter?
Well, we hope that someday it will. We hope that its interactions with conventional matter are just very, very weak, and therefore we haven't been able to detect it yet. For a long time, that was the status of the neutrino. The neutrino was a little particle that was predicted by particle physicists in the 50s, or maybe even before the 50s, actually. Yeah, before the 50s. With the annoying property that you couldn't detect it. But it existed, and it had mass, maybe not, maybe it was massless, but it had certain properties we understood very well, and we thought about it and built better experiments, and eventually we detected them. And now we know that the sun is spewing out neutrinos, and neutrinos are passing through our bodies all the time, and we detect them every day. There's neutrino experiments going on. So we're just saying the same kind of thing would be true with more particles that we haven't yet detected. I mean, at some level, we need to be a tiny bit humble. There's no reason why the particles that are easiest for us to see should be most of the stuff in the universe.
Okay, but it's still hard to understand why those we can see don't interact in any way, apparently, with those that we can't see.
Well, again, it could be very much like neutrinos. And what I mean very much like, I mean, we have very successful models of how particle physics works. And there's this famous statement that there are four forces of nature: the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. And of those four, the strong nuclear force and the electromagnetic force are just bloody obvious. It's very easy to see things that interact in that way. And almost every particle that we know interacts either through the strong nuclear force or through the electromagnetic force. The only counterexample is the neutrino, and it's been very, very hard to see. It only interacts through gravity and through the weak nuclear force. So if you had another particle that was heavier than the neutrino but also only interacted through gravity and the weak nuclear force, it would be a perfect dark matter candidate. And it's very, very plausible. It's just not a very big extrapolation from known physics. Unlike dark energy, by the way, dark energy is a separate category, which is a bit more mind-bending. But dark matter is really just one more heavy particle we haven't quite detected yet, even though it could be very much like particles we already have.
All right, where does dark energy come from, if not dark matter?
Well, dark matter was inferred from looking at what galaxies and clusters of galaxies do. They move around each other, they deflect light, they grow as the universe expands, and every single thing about them tells us that the total mass of a galaxy or cluster of galaxies is dominated by dark matter, not by ordinary matter. But more recently, we've been able to go beyond looking at galaxies and clusters to looking at the whole universe all at once, both sort of weighing the whole universe, determining the entire amount of energy in it, and also looking at its evolution through time, looking how it expands and how the expansion rate changes. And what we've realized is that in order to fit those new data, there must be stuff that is in between the galaxies and clusters. There must be stuff that is smoothly spread throughout the universe. So there's a lot more density at the center of the Earth than in the middle of interstellar space. And there's even a lot more density of dark matter in the solar system than there is far outside the galaxy. But dark energy is something that has the same density everywhere, the same amount for every cubic centimeter, whether it's right here in the room or very far away in between the galaxies.
Okay, so then dark matter does not have an equal distribution.
No, just like ordinary matter. There's a bunch of dark matter where there's a galaxy, and there's much less of it when you're far outside a galaxy.
On the other hand, dark energy is equally present everywhere.
That's what we think, yes. And
are these the forces? Yeah, okay.
It's the same density as a function of time as well. As the universe expands, ordinary matter dilutes away, right? Just as if you take a balloon and expand it, the density inside goes down because you're creating more volume.
Right.
But as you expand the universe, While the dark matter dilutes away and the ordinary matter dilutes away, the dark energy persists. So the amount of dark energy in every cubic centimeter of the universe doesn't grow or shrink as the universe expands. So it's really the same everywhere in space and the same everywhere in time. And that's a dramatic idea, but you come up with that one idea. You just say, okay, maybe there's something that's the same everywhere throughout space and time, and it fits a multiple set of observations. So there's really no wriggling out of it by now.
And everything is moving away from everything else, so that eventually, someday in the far distant future, we will look into the sky and we will see virtually nothing but blackness, yes?
That's the idea, yes. That's exactly right.
That's very
Things
depressing,
will
very
fade
depressing.
away, get more red and cold.
More red and colder. All right, Dr. Carroll, hold it right there. Dr. Sean Carroll is my guest. Eventually, the night sky will no longer be star-studded. I'm Art Bell. Very fascinating. Dr. Sean Carroll is my guest. And I think in a moment we'll ask him about the Big Bang. Is that really how it happened? That incomprehensible moment when something smaller than a quark, which I don't think we've still properly identified, became all that is. It seems so totally unreasonable to me. Dr. Carroll, back in a moment. I guess the current belief about the age of our universe is around 14 billion years or something like that, and still expanding it. It seems to get revised every now and then as yet another bright, no doubt, quickly rotating object in space is located. They add another billion years or so to how old the universe is. But at the beginning of it all, there was apparently this Big Bang. This moment when something so small that we can barely think about it became all that is. Doctor, is there any way that, well, I guess first of all, you do believe in the Big Bang scenario, right?
I do, yeah. I'm a big fan.
Okay. I'm a big fan. How is there any way you can explain to me how something that small, smaller than a quark, right?
Well, this is exactly the question. I mean, the physicists use the term Big Bang to refer to two slightly different things. One is, like you said, the Big Bang scenario, which says that the universe is expanding from an initially extremely hot, dense state into the large, dilute, cool state that we're in right now. And that scenario has been tested 7 ways from Sunday and is very firmly established. But then they also use the phrase Big Bang to refer to the moment at t = 0, when the classical theory that we have predicts that there's a singularity. That in fact,
now,
it's not
t meaning
time.
I'm sorry, t meaning time.
Time = 0, the beginning of everything.
Okay.
Yes.
All right.
Not just smaller than a quark, but literally zero size is the prediction. But the point is that nobody believes that. The point is that that is a point where the theory that we believe right now predicts that the theory itself makes no sense. So everyone knows that we don't know exactly what happens at that moment. It could be that somehow the universe came into existence. It could be that there was a pre-existing stage of the universe's history out of which our purported Big Bang arose, and we strictly have no idea.
Could what we call the Big Bang, and we imagine to be something coming from nothing, could it, for example, be the collision of two black holes?
Yes, it could be. That would require that there's some pre-existing space and time.
Right.
And in that space and time, something happened. Maybe two black holes colliding. I'm not a big fan of two black holes colliding, but there are other things that could happen in a pre-existing space-time that would cause what we call a baby universe to form. A little bubble of stuff could appear in space and time and pinch off and grow into its own universe. And that's completely in play in terms of scenarios for what happened at or before the beginning of what we perceive as our universe.
It's an awful lot easier to believe that than it is to believe that something that had no mass became all the mass.
Yeah, you have to be a little bit careful because, on the one hand, the universe doesn't care what we find easy to believe or hard to believe. It's just going to obey the laws of physics. But on the other hand, our laws of physics break down at that point. So it's perfectly okay to use our intuitions about what makes sense and what doesn't make sense to sort of make up plausible scenarios and then see if you can build them into respectable theories. We haven't done it yet, but it's an absolutely, it's something that people are very actively trying to do at the cutting edge of cosmological research right now.
Is there any area of research in your field that is closing in on what exactly did happen?
Well, closing in is a little bit of an optimistic way of putting it, because we don't know whether we're closing in until we've closed in. There is absolutely a set of people, and I'm one of them, who are writing papers about what could plausibly have happened before the Big Bang. Where could the Big Bang have come from? And
well,
again,
other than the collision of two black holes, what do you imagine?
Well, I imagine that there are quantum fluctuations. You know, quantum mechanics says that you can't pin things down to perfectly predictable states, and that includes space and time itself. So even in our universe right now, even as we're expanding and our universe is emptying out, there is dark energy, right? We believe that there is dark energy, which means even empty space has energy, and the universe will always keep expanding. It will never completely stop.
Right.
And that means that space and time in the far future of the universe are always going to be jiggling a little bit, always going to be fluctuating. And we could get lucky, and a fluctuation happens in just the right way to pop out a new baby universe from that pre-existing empty space.
Well, from our perspective, would that really be lucky or catastrophic?
It wouldn't be so bad from our perspective, because from the outside perspective, what we would see is the formation of a tiny black hole, which would then soon evaporate away. But if we were to go into that black hole before it evaporated away and do some quantum mechanical magic, we would come out the other side into a brand new baby universe. These are all things that we're allowed to speculate about, not at all anything that well-understood theories predict, but these are things that are, like I said, on the table for what could possibly be going on. So cosmologists get in a little bit of trouble because we have a really good theory. We have Einstein's general theory of relativity that describes what we observe in the universe right now to exquisite precision. And it's really good. We like this theory. It predicts, it explains the whole Big Bang that we know and love up to that point at the very beginning where it breaks down. And if the theory were right perfectly, then the universe would have a singularity at the beginning, and that would be the moment when everything began. Time and space came into existence. But the theory is not right at that point. As much as we know and love the theory today, when the curvature of space-time becomes infinitely large, the theory is not right, and there's no reason to think it is. So we have to be open-minded.
And does that open-mindedness include the possibility of intelligent creation?
It includes the possibility, but as far as theories go, that's not most people's favorite theory, no. It doesn't help with anything. I mean, our universe seems to just be following rules, and it seems much more satisfying to a scientist to find rules that it obeys all the way through, even before the Big Bang.
Can we ever know anything about, can we actually get to before the Big Bang? Is it doable?
Well, strictly speaking, I have to say I don't know, since we haven't come up with a theory yet. I would not be surprised if the answer is no. I hope that's not too many negatives. It's very possible that we can never get direct experimental evidence of what happened before the Big Bang. But what is possible is that we could have a theory that, on the one hand, made testable predictions, and we tested those theories really, really well, and tested those predictions really, really well, and at the same time, that theory told us unambiguously what happened before the Big Bang. That's what you have to aim for. We're not there yet. We're not going to get there in the next 2 years, but this was my prediction for what the big breakthrough would be in the next 50 years in cosmology. That 50 years from now, we would understand the Big Bang.
So we could be then, what we call the Big Bang could be the creation of a new bubble, a new universe. It could be that moment.
That's right. It could be nothing special in the whole history of the universe. There could be little bangs going on all over the place. It almost makes more sense, but I try not to care what makes more sense or not. I just try to follow what the theories are telling us could happen.
There are those who believe that if we found a way to travel in time, if we went back into time and did something that was a violation, killing dad or killing grandfather, whatever, that at that instant you would not cease to exist, you would continue to exist, but there would be a new bubble created, a new universe in which matters would unfold in a very different manner, different way.
Yeah, this is one of those things that it's hard to speculate about even in an informed way because we don't understand the complete set of laws of physics that would allow us to travel backwards in time. So it's like saying if 2 plus 2 equaled 5, then what would 7 plus 8 equal?
Yes, it's just another way out of a paradox, though, a more modern way of explaining how you might get away from a paradox.
It's a way, that's right. So there's different ways. One way to avoid those paradoxes is that time travel is not possible. That's the simplest way and sort of the most likely one. Another one is that you can travel back in time, but you cannot change anything. This is also, quite sensible that even though you think that if you were back there, you could do whatever you want, you still need to obey the laws of physics, and your past has already happened, and it's been determined. You can't change anything. Like you say, then there are more dramatic possibilities. One is that quantum mechanics becomes involved, and there's a different branch of the wave function, a different sort of quantum mechanical universe branches off. And now we're talking about stuff that is fun to think about, but really is completely unmoored from physics that we already understand.
Sure, way out there.
So it's just hard to make any sensible judgment about how likely it is.
What about other dimensions? Are you a believer in up to 11 dimensions?
I am. I think that extra dimensions that we haven't yet observed make perfect sense and are even sort of pointed toward by some of our favorite physics theories that we have right now. But people get a little bit the wrong impression when we start talking about other dimensions. It's not like another plane of existence or even another parallel realm. We're talking about dimensions just like we talk about the 3 dimensions of space here inside a room. If you're a piece of paper, if you live on a piece of paper and could never leave, you would think that space was 2-dimensional. Here in this room, we think it's 3-dimensional. We're talking now about a hypothetical universe where space would be 4 or 5 or 6 or 10-dimensional. And that universe could be ours if those extra dimensions exist but are curled up to be so tiny that we can't perceive them. And I think that's very plausible. That's one of the things that we're trying to test experimentally right now.
And so you would not expect to find, as you mentioned, any sort of parallel universe where there's a whole different set of things going on in the same space?
Not in the same space. It is quite plausible that very, very far away, in a place that would seem like a different universe, but is really just our universe, just far outside what we can perceive right now, conditions are very different. Even what we think of as the laws of physics are very different. The charges and masses of all the elementary particles are different. There could be a region of our universe very far away where space looks 6-dimensional instead of looking 3-dimensional. These are things that actually are not that far out in terms of the state-of-the-art of fundamental physics. We can talk sensibly about those things. We don't know if they're right or wrong, but they fit comfortably within a framework that we think is plausible.
You don't think dark energy could be mixed up with another universe, do you? And that would be the reason that we cannot reasonably measure it.
Well, we can reasonably measure it. We can't detect it except through its gravitational effect. But its gravitational effect is quite detectable, and we've measured how much there is. So,
yes, but we really can't detect dark energy as such. It's kind of like we're detecting the fact that something's there. But we can't detect that something directly. We're
That's
just
fair enough,
detecting
yeah.
the effect of it.
That is right. That is right. But we could say, if someone asks you how much dark energy there is, you can say there is 1/100th of a millionth of an erg in every cubic centimeter. That's a fact that we know about the universe if our theories are on the right track. And the existence of extra dimensions of space, curled up very tiny so that we can't see them, is one of the things that feeds into that number. So the existence of extra dimensions might play a very crucial role in determining why the dark energy has the size that it does.
Uh-huh.
That's something that people are taking very seriously. But what we would like is a formula. What we would like is a prediction that says, given what we know about the other laws of physics, here's how big the dark energy should be. We don't have that, or let me put it more accurately, the best formulas that we have along those lines give us answers that are wildly off from the number we actually observe. So this is a big puzzle that we're trying to understand. But we like puzzles because that means there's something we don't understand, and it's a clue towards a better theory that we don't yet have.
Are we closing in, a bad phrase again, on this theory of everything, this little formula that will eventually explain virtually everything? Is there going to be such a thing?
Well, you never know, and throughout human history, people have made fools of themselves by saying, oh, yes, we'll just dot a few I's and cross a few T's, and we'll have it all figured out. Very, very smart people, for that matter. And I should say that on the one hand, we do have a unique situation in fundamental physics, that we have a theory that is almost a theory of everything, namely the standard model of particle physics plus general relativity. These two theories together, up until a few years ago, explained perfectly every piece of data that we had about what was going on in the universe. Since then, there have been chinks in the armor with things like dark matter and dark energy, hints that there's something beyond the standard model of particle physics, and therefore, but that was perfectly expected. No one ever expected the standard model to be the final answer. But I guess the lesson here is that if someone did come up with a theory tomorrow or 5 years from now that did accord both with general relativity where gravity is concerned and with the standard model of particle physics where all the other forces and particles were concerned, it would not be completely crazy. It would not shake our foundations. We think that we have a pretty good grasp of what's going on. That would just complete the story. On the other hand, we could do an experiment at CERN next year that is completely divergent from that kind of understanding. We realize, oh my goodness, there's a whole realm out there that we haven't yet even begun to probe. So I'm very agnostic about whether or not you're close to the theory of everything. It's like asking whether or not the Russian dolls, as you open them, is this going to be the last one or not? Until you open it, you don't know.
And by the way, are you upset that all this has to occur at CERN, that we don't have an accelerator here in the United States that is doing this leading edge work?
Well, I'm more concerned that in the long run we seem to have lost our enthusiasm for doing basic research in other fundamental physics form. We should admit that particle physics at the energy frontier is expensive. It's expensive enough that not every country can have their own major accelerator. They should be international efforts, pooling our resources as much as we can. And so I'm not upset that the one that will turn on next year in Switzerland and France will be the leader. I'm upset that we're not doing everything we can to build the one that will come after that. There are excellent plans on the drawing board for doing that. It could plausibly be built in the United States, and there's some lip service given to doing it, but as a matter of reality, we're cutting our budgets for NASA's astrophysics missions and for the Department of Energy and things like that.
I know.
So it's worth doing because it doesn't lead to a better television or a better transistor radio, but it tells us what the universe is made of. It's the kind of thing that everyone can appreciate, and as a fraction of the money that we spend on things, it's really very, very tiny.
Do you think that some of the reason that in the United States the money is not readily being made available has to do with the fact that the further with this we go, the farther away from the possibility of God at the center of it all we get? This wouldn't be talked about a lot. We're at a break already, so darn it, hold tight, Doctor, and we'll be right back. Dr. Sean Carroll is my guest, and if this is not fascinating stuff, then, well, you're just not listening. That's all there is to it. We'll open phone lines when you get back. You know the portals, so if you want to enter and be prepared to ask a question, now would be a good time. I'm Art Bell. From my point of view, good afternoon, morning, or I suppose evening, depending on where you are around the world soundly covered one way or the other by this, the largest program of its kind in the world. I'm Art Bell. My guest is Dr. Sean Carroll, and your turn with Dr. Carroll is coming up. Just a couple of more itsy-bitsy little questions, and then we're going to open the phone lines. Keep it planted. Dr. Carroll, here in Southeast Asia, in Asia, I live in a country that is predominantly, overwhelmingly Christian. America is overwhelmingly Christian. Could it be, Doctor, that money for the kinds of things that we were talking about, accelerators and such, is not exactly forthcoming so quickly in North America because of that Christianity, because the answers that ultimately may come from this line of experimentation may provide alternate answers to God?
I don't think so myself. I think it's a complicated question. It's a good question. I think that in this particular case, the answers are a little bit more down to earth, a little bit more mundane than that. Basically, fundamental physics has been probing the nature of space and time and matter and where the universe has been coming from for a while now. And traditionally, people have been able to both be religious and support that kind of thing, or to not be religious and support that kind of thing. I haven't heard any, in when you talk to both policymakers and scientists at the funding agencies, the kinds of things you hear are not those kinds of things.
Those wouldn't be the kinds of things you would hear.
It might not be, but there is a public discussion going on. So if someone had an opinion that this isn't the kind of thing that you should be doing because of that reason, they wouldn't get very far unless they told somebody. I have heard some things like that. There was a famous example, and I don't know the exact quote, so you shouldn't believe me, where Al Gore was a little bit startled to think that particle physics was going to be telling us about the nature of the Big Bang, because that was religion's territory. And I think that there are some people who think that, but I don't get the impression from the actual people making the funding decisions that that's foremost in their minds. In fact, I heard a very elaborate talk from a senior official at the Department of Energy who was celebrating how physics was illuminating the same kinds of questions that religion had been asking for thousands of years. So you can spin it that way just as well.
I guess you can. And then, Jim, I get these questions on a computer as we go along with the program. Jim in Sandy, Utah, says, somewhat flippantly, when I daydream, a blue-collar gets into trouble. When your guest daydreams, he gets paid big bucks. Have we actually gained anything from his or any other scientist's daydreaming?
I think the bucks are perhaps not as big as he's imagining that they are. No one ever goes into theoretical cosmology and particle physics for the money. Let's put it that way. It's a lot of work. There's a lot of people who want to do this for a living who don't get to. But he raises a serious question. What good is it? Is it worth the money that we put into it?
Yes.
I think there's two answers. One is that there are plenty of good things that do come from basic research all the time that you can't possibly anticipate. It's not as if you gave Alexander Fleming a lot of money at some day in the past and said, make penicillin. You said, do some research and understand how things work better and see what comes of it. And that's how a tremendous amount of scientific progress is made. So the short answer is yes, a tremendous amount of good comes from people daydreaming. And the other answer is that even if it didn't, it would still be worth doing, because it's not that much money, and it is answering questions that we all care about, or at least many of us care about. We just want to know the answers when it comes to everything from where the universe came from to, how we evolved and what life is like deep underneath the sea and whether there's life on Mars and all of these questions. These are big box office, and for good reasons.
All right. Are you ready for some spooky interaction?
I'm ready.
Okay, here it comes. Wildcard line, Stan in Florida. You're on the air with Dr. Carroll.
Yes. Well, first of all, it's the idea of daydreaming. That's what makes us human, and that's what has made us, the dominant species on this earth. Anyway, one of the things that I wanted to bring up, you were talking about time travel and stuff. We look at what we call UFO interactions here on this planet, and understand, I'm retired Air Force. Back during the Israeli airlift in 1973, I was stationed in the Azores Islands, and everything that we were sending to Israel came through the Azores, which was an enormous amount of material. We had visits by UFOs not less than once a day. My car one night when I was going to work was flown over by a UFO buzzing our airport. Now you say, well, okay, the government doesn't believe in this. Then why did they send the team in when it was over to debrief all the people that worked on the flight line and every air traffic controller on that base on what they had seen?
Stan,
where this ties into time travel is that, the paradox, you say you can't go back and kill your grandfather, and still live and stuff like that. Okay, what if time travel is what we're experiencing in these UFOs? That our experience, is, future humans coming back and observing or gathering data. They're historians per se.
Okay, it's a worthwhile question. Let's pose it in a slightly different way. Dr. Carroll, there are enormous numbers of reports. Even our military, which is radar-tracked, unidentified craft that traverse our atmosphere at just 25,000 miles an hour and faster. And these cannot be ignored. I mean, there is a substantial amount of real evidence that there are things in our skies that are completely inexplicable, traveling at speeds and in ways that would turn humans into jelly. And I wonder if it's worth your comment in any way at all. Could we be visited? Are we perhaps being visited and just simply haven't proven it?
Yeah, I think that the time travel question is actually interesting in its own right, but it's a little bit separate from the UFO question, which as a scientist, the way that we think is to say, you're judging between two different hypotheses, and you have to judge which one better fits in with everything else that we know. And one of these hypotheses is that there are intelligent aliens who have super advanced technologies and are buzzing us in their UFOs, which we are able to detect occasionally on our radar screens, but nevertheless do not detect out there in their solar system or communicating via radio waves or any of the other ways that we can do it, and that these aliens have chosen to remain hidden from us, and that we do not see any evidence from their existence from other solar systems. Or you believe the hypothesis that there aren't any aliens there, and that these reports are some combination of misreadings and atmospheric phenomena and other planes that you didn't know about. And almost every scientist will come down on the side of saying that a combination of very mundane explanations are a more reasonable fit to these observations than to really believe there's a race of intelligent aliens who are hiding from us, but occasionally show up in eyewitness reports and radar reports.
Very well said. Until you've seen one yourself. First-time caller line. You're on the air with Dr. Carroll. Hi.
Hi, Art. My name is Bill, and I'm calling from Sault Ste. Marie, Michigan. My question for Dr. Carroll this evening is, back in physics, I learned that the law of conservation of energy and matter, that matter can neither be created or destroyed. Now, this is the first I've ever heard of dark energy. I'm wondering where the dark energy is coming to fill the expanding universe. I mean, it has to come from somewhere.
No, that's a great question. Very good. You're halfway to being a professional cosmologist right there, just by catching on to that. The very short answer to this question is that in an expanding universe, energy is not conserved. So it's true, you were taught when you took Physics 101 that energy is neither created nor destroyed, but you weren't taught about the expanding universe at the same time. And the rules change a little bit once you realize that space-time is curved and the universe can expand. And it's something that actually sort of has been tested in other parts of cosmology that we probe quite accurately. So when the universe expands and the dark energy remains a constant amount of energy per cubic centimeter, but the number of cubic centimeters goes up, it's true, the total amount of dark energy goes up. On the other hand, when the universe expands and photons, ordinary light, travels through the universe, that light loses energy because it's redshifted as the universe stretches the wavelength of the light. And therefore, the total amount of energy in photons is not conserved either. And there's just no law that says the total amount of energy in the universe remains a constant. Instead, there's a law that says, given a certain amount of expansion in the universe, here's how the energy will change. So if that expansion's zero, the energy would be constant. But you basically have to give up on your belief in the law of conservation of energy once you realize the universe is getting bigger.
All right. Bill in California, west of the Rockies, your turn.
Hey, good evening, Art. Good evening, Doc. How are you doing tonight?
Good.
Fine.
Thank you for taking my call. Hey, I got a theory that I've been talking to about. Actually, I called you once with it, Art, quite a long time ago, like 10 or so years ago. And it premises like this. Say for the sake of argument that we have a universe that exploded from a Big Bang, and it's essentially a ball-shaped thing. And if we draw a circle on a paper with a radius of 15 billion light years, put a dot on the outside representing a planet looking back at that, say 16 billion light years away from the center, and we're on that planet looking back at that particular circle, what will we see? And the answer I would say is nothing, because the light hasn't gotten there yet. But we would see or register quite a lot of mass. Perhaps we would see it as a black hole. So my first question is about the expansion possibilities of a black hole. And the second thing is about, well, let's say for the sake of argument that my premise is correct, what would happen when that black hole's event horizon finally hit the Earth?
Well, I think that I'm not going to make you very happy with my answer, because I'm sort of going to unask it, because the image of the Big Bang that we know and love as an exploding fireball expanding through space is not, I think, the right way to think about the Big Bang. In our part of the universe that we observe, forgetting for the moment about the possibility of other parts outside that we haven't yet observed, the Big Bang is not the expansion of some stuff into space. It's the expansion of space itself. There isn't any outside. There isn't any center point from which everything is expanding. The amount of space itself is getting bigger. So there's no edge. There's no middle. There's no edge. Every point is moving away from every other point.
I kind of understand that premise. I'm just kind of using the vision of a circle to kind of simplify things for myself. But if it was for the sake of argument to be in that situation, we would say kind of sort of that our universe was a black hole, and perhaps other black holes would be therefore universes. And when we're looking at when we're looking at a black hole, is an expanding universe. I mean, there's technically no space or time in these things to begin with. So,
well, there is actually space and time inside a black hole. The real difference is that in our universe looks the same everywhere on very large scales. So we look in all directions around us, and we see the relic leftover radiation from the Big Bang. In a black hole, there is a special direction. There's, toward the middle of the black hole, which is different than away from it. So our universe looks different from a black hole in the most basic feature, that it just looks the same all throughout space as far as anyone can tell.
Okay, east of the Rockies, Charles in Florida, your turn with Dr. Carroll.
Hi, I guess my question, I have to pose a question, would be if someone called you, and I know there's at least one other that's called into the show, that is down the path, or let's say in the orbit, of finding the everything theory, would you even listen to them?
Well, sure. It depends on what they had to say.
Okay.
Let me put it this way, and I said this before. If someone working somewhere had come up with a plausible and promising and innovative theory that was better than the theories that we already have, and typed it up and sent it to me, and I'd be very happy to promote this obviously brilliant idea. On the other hand, if someone thought that they had a theory that was better than anyone else's, but really didn't understand the current theories, the general relativity and the standard model of particle physics and quantum field theory, then I would ignore it. And there are a lot more people like that. So, I mean, it's hard to invent a new theory of everything, and it's impossible to invent such a theory until you've mastered the theories that we already know and love.
Well, I'm about as obscure as a clerk in a patent office. Okay, but I'll give you 3 teasers, to describe it all. It's a simplistic theory, of course, as Einstein said. And by the way, Einstein said that in science, without religion, that's being lame, and religion without science is blind. I got 3 teasers that'll make you think. Okay, first of all, in mankind...
Well, hold on a second, caller. Did Einstein say that, Doctor?
There was some quote very much like that. I don't know the exact details, but that was close enough, yeah.
All right, very interesting, caller. Go ahead.
Okay, I'll give you 3 teasers to make you think and maybe make you know that perhaps like this other gentleman who called in the show, we're both on the same road or path or orbit to the everything theory. First of all, in mankind senses, he's unable to determine certain things, but he is able to imagine with that wonderful attribute of imagination. First of all, there is no beginning or end. You see, mankind has a lifespan. The bird in the birdcage dies. His house pet dies. His TV goes on to blink. All he ever knows in his immediate surroundings is there's a beginning and end. But he has to learn there is no beginning or no end in anything in the universe. Okay, now with that in mind, I want you to remember when your mom and dad told you, as my mom and dad told me, that as you get older, time will seem to go by more quickly. Well, it's a scientific fact, and I can prove it, that science, time standard is changing. It's noticeable within our own life tenure as a human species. It's a stretching of time, oxymoron, time standard. What we're observing, and each generation observes in an escalating way, is that there's a time standard change. For instance...
Caller, we just don't have any more time. I understand where you're going, and I share with you the impression, the feeling that as you get older, time is going faster, but it in fact is not. Doctor, would you agree with that?
It's 1 minute per minute as the actual time goes by. There's, of course, a psychological perception of time, which is a more complicated question than that. But I also want to say something sort of in the background here, which is that I'm a big believer that science is for everybody. It's not just for people who have PhDs and so forth. Everyone should be able to understand ideas and think about them and appreciate what is going on in the universe. But coming up with new ideas is hard, and you should have a little bit of respect for the generations and generations of well-trained people before you. And if you want to come up with a new idea, that's great. But you should first figure out what the old ideas already are. And everyone should, take their spare time and pick up books on general relativity and cosmology and particle physics and learn some
go
stuff
from there.
Already discovered about the universe, because there's great stuff.
Hold it right there, Doctor. We'll be right back. By the way, Want to Take a Ride comes directly from the movie Contact, my favorite movie of all time. It's making the rounds on the pay channels again right now. And if you've never seen Contact, or even if you have, go back and see it again. God, what a movie. Dr. Carroll's website is preposterousuniverse.com. That's preposterousuniverse.com. I'm fairly sure we've got a link up on coasttocoastam.com right now. I see no books as yet. I thought in his world it was publish or perish. We'll ask about that when we get back in a moment. Why the name preposterousuniverse.com?
Well, the phrase preposterous universe is one that I came up with to emphasize the fact that on the one hand, we have over the last 10 years done an amazing thing. We figured out the inventory of the universe. Ordinary matter, and dark energy, we know what proportions it is. On the other hand, it's not what we would have guessed. This is not as simple and as elegant as the universe might have chosen to appear to us. So there's something preposterous about it, which, like I said before, is something that physicists love because it means there's something we don't understand, and we're trying our best to invent better theories in which all the preposterousness will make perfect sense.
In other words, more work.
Oh, yes. We're not finished yet.
You have not yet written a book that I can tout. I
have written a book.
You have?
But sadly, it's a graduate-level textbook. You're welcome to tout it, but I wouldn't really recommend it unless you're in graduate school. It's called Space-Time and Geometry.
Oh.
Someday I will write a book that will be for my mom to read.
It sounds like you ought to. You're obviously capable of explaining things in a way that I can almost understand. The exact Einstein quote, by the way, courtesy of Dennis in Plover, Wisconsin, is science without religion is lame, religion without science is blind. Would you agree with that or argue with it?
No, I wouldn't agree with it, actually. And in fact, I think that we should be very cautious when interpreting Einstein talking about religion, because he had he didn't always mean the same things that the rest of us mean when we talk about God or religion and so forth. Einstein had a sense of wonder at the universe, which he spoke about in religious terms, which is very different from a more conventional church-going kind of religion. But I don't think that... I think that what he was getting at is the fact that science by itself doesn't tell you how to live your life. Science tells you how the world works, tells you the laws of nature, but how to judge good and bad, or beautiful and ugly, or right and wrong is not contained in any amount of scientific investigation you might do. It's going to come from somewhere else, whether it's from religion or from human agreements and careful considerations. Different people have different ideas, but science just tells you what happens.
Well, that's fascinating. Wildcard line, Mary in Hazleton, Pennsylvania. You're on with Dr. Sean Carroll.
Hello, Art, and hello, Doctor.
Hello.
Pleasure. I'm having trouble here. I'm taking a college course in physiology and anatomy, and I'm studying cells right now. And the dark matter, is dark matter when two atoms collide and bond, and it sort of makes a mistake and dark matter comes out, or am I totally wrong?
That's a very colorful idea, but it's not really right as far as the dark matter is concerned. If only it were that easy. But if you're studying cells, then you know that those cells are made of molecules, And if you keep digging down, those molecules are made of atoms, and those atoms are made of electrons and protons and neutrons, and those protons and neutrons are made of quarks. And as far as we know, that's where the layers stop. But in that whole list, dark matter is nowhere there. Dark matter is something else, some other kind of particle that we haven't figured out yet. We haven't made it in the laboratory or detected it directly here on Earth. But we know it's there because it has a gravitational effect, because there's many, many, many such dark matter particles out there. So one of the big projects over the next 10 years is to detect the dark matter particles directly, to make them at particle accelerators like the one at CERN in Geneva that we've been talking about, and also to build very sensitive detectors deep underground, far away from cosmic rays and other interference, that can actually feel it when an individual dark matter particle bumps into one of the atoms in the detectors. So this is a headline to look out for in the newspapers over the next 10 years. Physicists detect dark matter once and for all. That's something we're all hoping for.
Dr. Carroll, Nikola Tesla was working on energy essentially from the ether, from air, from nothing. Energy that I guess he didn't fully understand, or maybe he thought he understood it. I don't know. Does dark matter and dark energy represent a future of Nikola Tesla's dream come true and our energy problems essentially solved?
Well, all I can say is that I would be extremely surprised if that were the case. The dark energy in particular is sort of the most useless kind of energy there can possibly be. You know, if you imagine having a gallon of water, if that gallon of water is at the top of a mountain, you can do something useful with it, because as it comes down the mountain, as it rolls down, you can put a little flywheel there and extract energy from it. But once the water is down in the valley, it's useless to you in terms of getting energy out. Mm-hmm. And all the dark energy is down at the bottom of the valley in this particular metaphor. So the fact that the dark matter and the dark energy are very hard to interact with at all, and the fact that, especially for the dark energy, their form of energy is kind of useless, would make it extremely, extremely surprising to me that we will ever tap into them as practical energy sources. But I don't
we better find one pretty soon. West of the Rockies, you're on the air with Dr. Sean Carroll. Hi.
Hey, Art. Hey, Sean. How you guys doing?
Good.
Hey, this is Dave. I'm sitting here alone in the dark at I'm a security guard at a cement plant. You know what? I just happen to think of something. I've been waiting to hear somebody say it, doctor, but they haven't hit on it, and it's something that kind of irks me. Okay, when people think of a black hole, okay, they think of the term hole means something you can go through. Okay, so okay, oh my gosh, what's on the other side of a black hole? What if we go through a black hole? Are you going to be in an alternate universe? No. See, what's going to happen is, a black hole is not actually a hole at all, as far as I understand. I may be wrong, and I'm kind of asking you this, but rather a collapsed star or something of that sort. Let's say it's it could be anything you said, but let's say it's a star, for example. It's collapsed down to a massive thing that weighs the same as it did, before, but just the size of a golf ball. You are not going through that. You will go into that, And they say, well, what about the event horizon? Okay, well, the event horizon simply is just the point of no return where you cannot escape the gravitational pull, and you are going to go slamming into that thing. And, but you are not going to come out the other side of it. Is that correct or not? And Art, real quick, I want to get your okay to send you some pictures of an orb, some orbs, and a story behind it. I'll go ahead.
Okay, all right. Feel free to send those along. In terms of the black hole, you want to take any of that on, Doctor?
Yeah, I think that actually everything that the caller said is right on the money. He could be giving a guest lecture to my general relativity class, because the black hole, we think from the metaphor, from the words that are used, as it's a hole you come into and then go out of. But it's not. The black hole is a point of no return. It's a region of space where if you enter it, you can never come back out. But what happens when you do enter it is that you are driven inexorably to a singularity, to a point where space-time is infinitely curved and the gravitational field will rip you apart. And we don't understand that singularity, just as we don't understand the purported singularity at the Big Bang. So I can't tell you exactly what happens there, but every indication of things that we understand are that bad things happen. You don't pop out in some other part of the universe. You get ripped to shreds.
Did you happen to see the movie Contact?
I did.
Mm-hmm.
Do you know the story about Carl Sagan and Kip Thorne?
I do.
The movie, the book Contact, actually spurred a lot of research in theoretical physics on trying to see whether or not time travel was plausible.
Mm-hmm. Is it in that manner? In other words, might wormholes be used for time travel?
Well, wormholes are a little bit different than black holes in a couple ways. One is that they may or may not exist. Black holes are firm predictions of gravity as we understand it. Wormholes are much more speculative. But what it would be is if you take advantage of the fact that space-time is curved, to imagine that there are shortcuts through space and time. You can zoom in one direction and pop out very, very far away without really seeming to traverse a very large distance. And if Einstein says that space and time are mixed up, then if you can traverse very large distances very quickly, you can traverse time in interesting ways and maybe even go backwards. So the answer to your question is just a big maybe right now as to what is feasible in the real world. We can write down pictures of space and time that make it look as if you could travel backwards in time. Whether or not you could actually create such a situation according to the laws of physics, we don't really know the answer.
Doctor, do we have an Einstein alive on Earth now?
No. Einstein's dead. We have lots of other people who are really smart in their own ways. I mean, Einstein was not Isaac Newton. Isaac Newton was not Galileo, and Galileo was not Aristotle. Every new genius is new in their own way. We have some incredibly smart people coming up with incredibly good ideas, but success in science is teamwork between an incredibly smart idea and the universe cooperating. So we'll have to wait to see when someone is really going to make a breakthrough that the universe agrees is a good way to act.
All right, east of the Rockies, John in Nashville, you're on with Dr. Carroll.
Good morning, Art. Good to hear you. And Doctor, man, I hope I don't sound argumentative, but apparently you've never met Albert Einstein yet. You're speaking for his personal religious beliefs. Let's say, for instance, I've heard you mention a quark, and I guess Michio Kaku and you believe that the universe is a result of an exploding quark, which was all matter in the universe in this tiny singular piece of whatever it was.
I don't.
That exploded
caller, hold
and
on.
created
He didn't.
the universe.
Caller, he didn't say that. I'm the
Okay.
one.
Well, let me just ask this, Art. If the universe is a result of a Big Bang, what caused the Big Bang? There's no such thing, Art, and I believe that you know it, as an uncaused cause. So if it is a result of an explosion, what was the cause?
Okay, that's the one question I think Dr. Carroll's already said he can't answer. Is that correct?
Well, I think it's a good question in some sense, but I will change the rules of the game out from underneath the caller by saying that there's plenty of uncaused causes. The language that we use when we talk about causes is stuff that you and I, make sense to us in our everyday lives. If you push something and it moves, then the cause of it moving was that we pushed it. And Aristotle and Plato would have said that the laws of physics work that way too. But we know better now. We know since Galileo and Newton and Einstein and other people that the laws of physics are a set of equations, and the stuff in the universe just solves those equations. There's no causes and no effects. There's just stuff doing what it should do according to the laws of physics. And the idea of cause is something that's convenient to us on an everyday thing, but it's not fundamental. It's not deep down there in the laws of physics. And when it then comes to the Big Bang, I don't know whether the Big Bang was the beginning of the universe or whether it came from some pre-existing stuff. But in neither case is there any necessity that there was something out there causing it. It could have just happened.
Going back to his initial comments, what do we actually know about Einstein's religious beliefs or lack of them?
Well, Einstein had sort of subtle and complicated religious beliefs. And I don't want to speak for his religious beliefs, except to say that he was very comfortable himself using religious language in ways that didn't always correspond to a traditional religious belief. He grew up Jewish, and he often would say things like his interest was in figuring out God's thoughts. But as far as I can tell from having read a lot of what Einstein wrote, what he meant by that is he wanted to know the laws of physics. He thought, that those two things were more or less interchangeable, that God had, the vision of God to him was sort of the beauty of the way the universe works. And I don't want to go into the details of what he meant by that, because I don't have the ability to speak for what he meant. But he wasn't a church-going kind of guy either. And finally, it doesn't really matter. Einstein was very smart, but he was wrong sometimes, he was right sometimes. We have to figure out for ourselves how we should think about the universe.
Okay. Wildcard line 3, Mike in Ohio. You're on with Dr. Carroll. Hi.
Good evening, Art, Dr. Carroll. Dr. Carroll, in the Christmas Carol, when Scrooge is taken by the ghost of Christmas past, he could watch, but he wasn't able to interact. And Dr. Carroll, since observation affects our experiments, if we traveled out 10 light years and erected a giant reflector, and we used a super telescope to see our reflection 10 light years out, if this let us see 20 years into the past without being able to, say, change that past, would this observation have any more of an effect than, say, watching an old movie?
Well, I think that there's a short answer, which is no. It would have exactly the same effect as watching an old movie. We record things that happened in the past, and we observe those recordings, and they don't affect what actually did happen. And that's true whether or not it's an old movie or a DVD or a telescope put 10 light years away.
Would this qualify as a type of time travel?
In a sense. It's one of the interesting things about time is that the past exists as our memory of it, and this is not my idea. This goes all the way back to St. Augustine, who, in the 4th century was talking about the nature of time and came up with some very clever insights. And one of his quotes was, "The past is present memory." That the past that we think of is left behind in little records of our present state of the universe. And that's one of the aspects about time that is fascinating, because we don't have a future memory. We have records of the past, but not of the future. And why is that? And that's one of the things that physics doesn't quite understand right now. So,
if we took the reflector.
Sorry?
If we took the reflector out far enough, would it allow us to, say, see the dinosaurs? No, because the light that was emitted when those dinosaurs were there is moving away, and we can't ever catch up to it.
That's right. It's far gone. So we would have to travel faster than light, and I suppose we could travel faster than light and get out to a point where, of course, it'd be too far away to look back, but if you could, yes, then you would see the dinosaurs, but that would require faster than light travel, which I guess...
That's right. So if you had a wormhole lying around, you could do it. But I don't know of any such wormholes. So,
have you done many interviews like this, Dr. Carroll? I've not heard you before.
I've been on the radio a couple times, but this one is sort of the longest and most in-depth, which is good, because you get time to explain yourself a little bit more.
You're very good at it.
Well, thank you.
All right. Very quickly, first-time caller line, James in Chico, California.
I wanted to ask the doctor, to go back to quantum entanglement, if two people were to observe this particle and one was spinning clockwise, the other counterclockwise, and one was able to affect theirs to spin in the opposite direction, would the other one immediately spin in the opposite direction as well?
Well, I think that you put your finger on exactly the issue, but it's an issue of words. The correct way to say it really is what I said, which is that if one is observed to be going counterclockwise, then you know for a fact that if the other person observes theirs, it'll be going the other way.
See, that's the part I'm not going to understand, because there should be communication, Doctor. There should be communication possible. We'll do another show, and I'll eventually understand that. We're out of time. That's it. We're done. It was wonderful. You're a great guest. Thank you for being here.
Thank you for having me on the show, Art. Thanks to you.
Dr. Carroll. Good night.
Good night.
Ladies and gentlemen, I've got a 3-day weekend coming up, meaning I'll be here Friday, Saturday, and Sunday next. Until then, I bid you a wonderful week ahead. From Art Bell in Manila, good night.